Hello, traveler of time and thought. No matter where you are, whether it's day or nighttime, glad you're here. Welcome to Space Mirage. In this episode, we're exploring these space mysteries still haunt scientists, softly and slowly. So, lie down, plug in your earphones, close your eyes, and let science help you drift off. The universe, an ever-expanding tapestry of galaxies, stars, planets, and myriad forms of matter and energy, has captivated humanity for centuries. Modern cosmology tells us that it began approximately 13.8 billion years ago with the Big Bang, a colossal event that ignited space itself. From that moment, the fabric of the cosmos has been stretching outward. Weaving the vast cosmic web we observe today, remarkably ordinary matter, the stars, planets, and living beings we know accounts for only about 5% of the universe's total mass energy. The remaining 95% is composed of dark matter and dark energy, invisible forces that shape cosmic structure and drive expansion, yet remain elusive to direct detection, spanning over billions of light years. The universe contains an estimated 2 trillion galaxies, each hosting billions of stars and untold planets. This staggering enormity offers a humbling perspective on our own place in the cosmos. The laws of physics, uniform across space and time, govern everything from the intricate dance of subatomic particles to the life cycles of stars and the motions of galaxies. These principles enable scientists to predict phenomena with astonishing precision, from planetary orbits to the behavior of black holes, those enigmatic entities whose gravity is so intense that not even light can escape. One of the most tantalizing discoveries in recent decades is that the universe's expansion is accelerating. Observations of distant supernova revealed that dark energy, a mysterious repulsive force, overcomes the gravitational pull of matter, driving galaxies ever farther apart at an increasing rate. This insight profoundly affects our understanding of cosmic fate, suggesting a future of a cold, dilute universe where galaxies drift apart indefinitely. The Big Bang theory remains the cornerstone of modern cosmology. It posits that the universe originated as an extremely hot, dense point, roughly 13.8 billion years ago, and has been expanding ever since. 3 key lines of evidence support this model. Cosmic microwave background, CMB, in 1965, Arno and Robert Wilson accidentally discovered a faint uniform glow permeating the sky. This CMB radiation is the afterglow of the early universe, a snapshot from just 380,000 years after the Big Bang, confirming its hot, dense origin. Galactic redshift in the 1920s. Edwin Hubble observed that distant galaxies are receding from us, and the farther away they are, hotter universe. Light element abundances. Big Bang nucleosynthesis predicts the primordial formation of hydrogen, helium, and lithium. In the first few minutes after the Big Bang, the observed abundances of these elements closely match theoretical predictions, further validating the theory. Despite its successes, the Big Bang framework leaves profound questions unanswered. What preceded the Big Bang? A brief period of exponential expansion in the universe's first fractions of a second. Inflation smooths out energy and matter, explaining the remarkable uniformity seen in the CMB dot in its infancy. The universe resembled a seething soup of particles and radiation, too hot and chaotic for atoms to exist. As it expanded and cooled, quarks combined into protons and neutrons, which in turn fused into the simplest nuclei, primarily hydrogen and helium, through nucleosynthesis. Gravity then took the reins, drawing matter together to form the first stars and galaxies. These stellar furnaces forged heavier elements in their cores and dispersed them through supernova explosions, seeding the cosmos with the building blocks for planets and ultimately life. Today, galaxies trace a vast web-like structure with clusters and filaments interspersed by immense voids. The universe's expansion continues, propelled by dark energy. And its ultimate destiny, whether a big freeze, big rip, or something altogether different, remains one of cosmology's greatest mysteries. The first second after the Big Bang presents a timeline of incredible transformations that laid down the fundamental structure of our universe. Imagine the universe at its inception, an unimaginably hot, dense point. Within a fraction of that first second, the universe began expanding rapidly in an event known as inflation. stretching far beyond the realms of our comprehension and setting the stage for everything that would follow. This initial expansion was so rapid that, in less than a blink of an eye, the universe grew from smaller than an atom to a size larger than a galaxy. As it expanded, the temperature fell, allowing the fundamental forces of nature to separate. During the first tiny fraction of a second, gravity broke away from the grand unified force, marking the first major transition in the early universe. As the cosmos cooled further, the strong nuclear force responsible for holding atomic nuclei together separated from the electroweak force, itself a combination of the electromagnetic and weak nuclear forces. This separation marked the universe's transition from a state where all forces were unified to one in which the distinct forces we observe today began to emerge. Within that first second, the universe cooled enough for quarks the building blocks of protons and neutrons to start combining initially free in the extreme temperatures. These quarks began to bind together as expansion and cooling progressed, forming protons and neutrons in a process known as baryogenesis. Simultaneously, the universe was filled with a dense hot plasma of quarks, electrons, and neutrinos. As it continued to expand and cool, interactions between these particles changed. Quarks combined into protons and neutrons, which would eventually form the nuclei of the first elements. By the end of that first second, the universe, while still incredibly hot and dense by any modern standard, had cooled sufficiently for the basic forces of nature to assume their present forms, and for the first building blocks of matter to solidify into existence. The stage was set for the next phase of cosmic evolution, leading toward the formation of atoms, stars, galaxies, and eventually the complex structures we observe today. This rapid sequence of events not only illustrates the dynamic nature of the universe's birth, but also highlights the intricate interplay of forces and particles that underpin everything we know. Quarks are the essence of the matter that makes up the world around us, yet they remain shrouded in the mysteries of quantum physics, a field that fascinates and perplexes even the most seasoned scientists. To grasp their nature, imagine quarks as the fundamental building blocks of matter, smaller than atoms, protons, or neutrons, and crucial to the universe's composition. These particles are so minuscule and elusive that they cannot exist independently. In nature, they're always found in groups, binding together to form larger particles like protons and neutrons, which in turn make up atomic nuclei. The story of quark formation takes us back to the universe's immediate aftermath during a period known as the quark epoch. This epoch occurred within the first microsecond, 1/millionth of a second after the Big Bang, when the cosmos was so hot and dense that recognizable particles could not yet exist. Temperatures reached trillions of degrees, and matter existed as a quark-gluon plasma. In this plasma, quarks and gluons, the glue that holds quarks together, moved freely in a soup of primordial energy. As the universe expanded and cooled rapidly, the strong nuclear force finally took effect, allowing quarks to combine into composite particles. Protons and neutrons, the most stable and familiar baryons, became the essential components of atomic nuclei. This crucial step in the cosmic recipe binding quarks into protons and neutrons set the stage for the later formation of atoms, stars, planets, and life itself. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. But for protons and neutrons, only up and down quarks are directly involved. Gluons are the carriers of the strong force, acting as a powerful glue that holds quarks together despite their tendency to repel each other due to their charges. As the universe cooled from its initial fiery state, it crossed a threshold temperature that allowed quarks to start combining, a momentous event occurring approximately 1 microsecond after the Big Bang. This cooling period allowed the strong nuclear force, one of the 4 fundamental forces of nature, to dominate over the thermal kinetic energy that had kept quarks apart. When this happened, quarks began to stick together in stable groups known as hadrons. Protons and neutrons are types of hadrons. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The specific combination of quarks determines the properties of the particle, such as its charge. Protons are positively charged, and neutrons are neutral. This distinction plays a vital role in how atoms and molecules, the building blocks of matter, are formed and interact. The formation of protons and neutrons from quarks was a critical step in the early universe's evolution. It marked the beginning of the end for the quark-gluon plasma state and the start of a universe filled with matter as we know it. Once protons and neutrons formed, they could begin to come together to form the nuclei of the simplest elements, a process known as nucleosynthesis. This sequence of events set the stage for the chemical complexity necessary for stars, galaxies, and life to eventually emerge as we continue to unravel the universe's early moments. In the cosmic saga, these forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force as the architects of the universe, sculpting the raw materials created in the aftermath of the Big Bang into the complex structures we observe today. In the universe's first moments, all forces were unified into a single force. As the universe expanded and cooled, this unified force began to break apart in a process known as symmetry breaking. The first force to separate was gravity, which plays a crucial role in shaping the large-scale structure of the universe. By influencing the motion of galaxies and galaxy clusters, despite being the weakest of the four forces, gravity's influence grows with mass and distance, making it the dominant force on a cosmic scale. Following gravity, the strong nuclear force separated. Overcoming the repulsive electromagnetic force between positively charged protons, it was during this separation that quarks began to combine into protons and neutrons, as previously described. The strong force ensured that these particles could form stable nuclei, setting the stage for the creation of the first atoms. The weak nuclear force and electromagnetism were the next to differentiate as the universe continued to cool. The weak force is key in nuclear fusion and radioactive decay, playing a vital role in the life cycles of stars and the synthesis of elements heavier than hydrogen. Electromagnetism, on the other hand, governs the interactions between charged particles. It is the force behind light, electricity, and magnetism, shaping the behavior of atoms and molecules, thus the chemistry that underpins all life together. These forces dictated the universe's evolution from a homogeneous soup of particles to a structured, diverse cosmos filled with galaxies, stars, and planet sand, ultimately life. They determined the formation of the first hydrogen and helium atoms in a process known as recombination, leading to the universe's transparency to light and the release of the cosmic microwave background radiation, a relic from this era that provides us with a snapshot of the infant universe. The interplay between these forces also drove the formation of stars and galaxies. Gravity pulled matter together, while electromagnetism and the nuclear forces governed the internal processes of stars and generates the heavier elements essential for planets and life. Delving deeper into the mysteries of the universe, we pivot our attention toward the formation of the very first atoms, a seminal event that marked a turning point in the cosmic narrative. This process, known as recombination, occurred approximately 378,000 years after the Big Bang. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. As the universe expanded, it cooled, allowing the first atoms to emerge. Hydrogen, the simplest and most abundant element, was the first to form, consisting of just one proton and one electron. It marked the dawn of a new era in cosmic history. Soon after, helium atoms emerged, slightly more complex, with 2 protons, 2 neutrons, and 2 electrons. These elements laid the foundation for the chemical diversity we observe today. With atoms now stable, they began to gravitate toward each other, slowly building the first stars and galaxies. This era set the stage for the complex chemical processes that would eventually lead to the monumental formation of atoms. Came the birth of the first molecules, a transition that laid the groundwork for the universe's chemical complexity. As expansion and cooling continued, conditions became favorable for hydrogen and helium atoms to interact. Hydrogen, with its single electron, readily bonded with another hydrogen atom to form molecular hydrogen H. Though simple in structure, H played a pivotal role in early chemistry. It acted as a coolant, more efficiently under gravity, and thus leading to the formation of the first stars. In these stellar crucibles, the first heavy elements were forged elements that would later give rise to the rich chemical tapestry of planets, asteroids, comets, and all living organisms. The exact timing of molecular formation remains under study, but it likely occurred a few 100,000 years after the Big Bang, soon after atoms appeared. This era set the stage for the intricate interplay of forces that shaped the universe's large-scale structure from galaxies to planet sand ultimately made life possible. Hydrogen and helium emerge as the foundational elements of the early cosmos. In the aftermath of the Big Bang, these two elements dominated the universe's composition. Hydrogen, with its single proton and electron, formed the bulk of early matter. Helium, slightly heavier, was the second most abundant. Their simplicity made them critical building blocks for all subsequent elements and molecules, synthesized within stars. Hydrogen's importance extended beyond mere abundance. It fueled the first stars, population 3 stars, which were massive, hot, and short-lived, but essential for forging heavier elements via nuclear fusion. When these stars exploded as supernova, they seeded the cosmos with carbon, oxygen, iron, and other heavy elements, paving the way for new stars, planets, and, ultimately, life. Stellar evolution. Stars fuse hydrogen into helium in their cores, releasing vast energy and light, then later fuse helium into heavier elements, enriching the universe's elemental diversity. Moreover, the primordial ratio of hydrogen to helium provides critical insights into the early universe's conditions and strongly supports the Big Bang theory. Observations of this ratio, alongside the cosmic microwave background radiation, offer compelling evidence of the universe's hot, dense origins. Building on our journey through the cosmos, we arrive at another cornerstone of cosmology, the cosmic microwave background, CMB radiation. Essentially, the afterglow of the Big Bang. The CMB bathes the universe in ancient light, providing a snapshot of the infant cosmos at roughly 380 years old. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson. The CMB is pivotal evidence for the Big Bang theory, offering a window back in time when electrons and protons combined into neutral hydrogen atoms during recombination. Before recombination, the universe was a plasma in which photons scattered off charged particles constantly. As the universe expanded and cooled, photons decoupled from matter and traveled freely, rendering the universe transparent. Over billions of years, their wavelengths stretched into the microwave band, creating the CMB we detect today. The significance of the CMB lies not only in confirming the Big Bang theory, but also in the detailed information it provides about the early universe's conditions. Tiny temperature fluctuations, mere millionths of a degree, revealed the density variations that served as seeds for all current cosmic structures, from galaxies to galaxy clusters. Measurements of the CMB by missions such as COBE, WMAP, and Planck have led to precise determinations of fundamental cosmological parameters, including the universe's age, about 13.8 billion years, and its composition. Approximately 5% ordinary matter, 25% dark matter, and 70% dark energy. Venturing further into the cosmic narrative, we see how the CMB underpins the Big Bang theory. It paints a picture of an extremely hot, dense early universe that expanded and cooled, forming neutral atoms and allowing photons to journey unimpeded. An afterglow we observe today as the cosmic microwave background. Detailed analyses of its temperature anisotropies confirm predictions of Big Bang cosmology, reinforcing our understanding of the universe's origin and subsequent evolution. The observations made by missions such as COBE, Cosmic Background Explorer, WMAP Wilkinson, Microwave Anisotropy Probe, and Planck have provided extraordinarily precise measurements of the universe's age, composition, and expansion rate. These data match the predictions of the Big Bang theory remarkably well, reinforcing its validity. For example, the slight anisotropizany irregularities in the CMB map the distribution of matter and energy in the early universe. According to the Big Bang model, the cosmos should have been largely uniform, with only minor fluctuations that eventually grew into galaxies and larger structures. The existence of the CMB and the detailed properties it exhibits are thus in strong agreement with theoretical expectations. offering compelling evidence that our universe indeed began in a hot, dense state and has been expanding ever since. Delving into the CMB has opened new vistas in our understanding of cosmology. This faint afterglow from the Big Bang serves as a cosmic treasure trove, revealing the infancy of the universe and its subsequent evolution. One of the CMB's most profound contributions is confirming the universe's age. Precise measurements of its temperature fluctuations indicate an age of approximately 13.8 billion years. This empirical anchor provides a concrete timeline for cosmic history. Composition: detailed analysis shows it consists of roughly 5% ordinary matter, the stars, planets, and living beings we can see, about 25% dark matter, an unseen substance that exerts gravitational pull but does not emit light, and approximately 70% dark energy, the mysterious force driving the universe's accelerated expansion. These proportions reveal the dominance of dark matter and dark energy in cosmic dynamics. Moreover, the CMB has shed light on the geometry of space. Lines, in this model, neither converge nor diverge, impacting our understanding of cosmic shape and expansion. Studies of the CMB have also bolstered the inflationary theory, which posits a brief, exponential expansion in the first fraction of a second after the Big Bang. Early growth, smoothing out irregularities while leaving the seeds of structure behind. Beyond confirming established theories, the CMB invites exploration of new physics beyond the standard model. Anomalies, such as the so-called cold spot, or slight discrepancies in the CMB's temperature fluctuations, continue to spur research, suggesting that our current understanding of the universe may yet expand further as the afterglow of the Big Bang faded. The universe entered a period known as the Cosmic Dark Ages, a time lasting from roughly 380,000 years to about 1 billion years after the universe's inception. During this epoch, the cosmos was filled with a dense, cooling fog of neutral hydrogen gas, rendering it opaque and, in effect, invisible to the wavelengths of light our telescopes can now detect. Without stars or galaxies to illuminate it, this era stands as an enigmatic chapter in cosmic history, a stretch of time when the universe was eerily silent and dark. These dark ages were critical in the universe's evolution, laying the groundwork for the first stars and galaxies. As cosmic expansion proceeded, primordial gas began to clump together under the relentless pull of gravity. In regions of slightly higher density, hydrogen clouds collapsed to form the universe's first stars, known as population 3 stars. Unlike the stars we observe today, these pioneers were massive, luminous, and short-lived, composed almost entirely of hydrogen and helium. The intense nuclear reactions within these stars eventually reionized their surroundings, piercing the opaque veil of the Dark Ages and ushering in a new era of transparency and light. This phase transition, called cosmic reionization, marked the end of the Dark Ages and set the stage for the rich tapestry of cosmic structures we see today. The light emitted by these first stars and nascent galaxies began to travel across space, progressively illuminating the once dark universe. For astronomers and cosmologists, this period holds invaluable clues about the formation of the earliest cosmic structures and the elusive nature of dark matter. Studying the Dark Ages poses significant observational challenges. The glow from that time is exceedingly faint and often redshifted beyond the reach of conventional instruments. However, advances in technology, particularly next-generation telescopes, are beginning to pierce this veil. Observations of distant quasars, early galaxies, helping us understand the fundamental processes that have shaped the universe from its infancy to the present. Emerging from the Dark Ages, the universe embarked on a transformative journey, culminating in the birth of the first stars and galaxies, roughly 100 million years after the Big Bang. Initially, the cosmos was a homogeneous soup of hydrogen and helium gas, yet small fluctuations in density, perhaps amplified by the gravitational scaffold of dark matter, created pockets where gas was slightly more concentrated. Gravity pulled these clouds inward as they grew denser and hotter. Nuclear fusion ignited at their cores, giving birth to colossal first stars. These population 3 stars burned intensely and briefly, but their light ended the cosmic night. These first stars did not shine in isolation. Under gravity's relentless pull, they clustered together to form the earliest protogalaxies, smaller and less structured than modern galaxies. Yet the seeds from which today's spirals and ellipticals would grow. As these stars aged, they forged heavier elements: carbon, oxygen, iron that had not existed before. In their spectacular deaths as supernova, they expelled these elements into space for future generations of stars, planets, and, ultimately, life. The formation of these early stars and galaxies set in motion a complex web of interactions that would. Radiation from the first stars continued to rayonize the surrounding medium, clearing the residual fog and making the universe increasingly transparent to light. This reionization process unfolded gradually from about 150 million to 1 billion years after the Big Bang, transforming the cosmos into the starlit expanse we observe today. Even as light illuminated the universe, an invisible scaffold guided its structures: dark matter, comprising roughly 85% of all matter. Dark matter interacts only through gravity, making it invisible to our instruments. Its presence was first inferred from gravitational effects. Galaxies spin too rapidly to remain bound by visible matter alone, and clusters of galaxies exhibit gravitational lensing that betrays unseen mass. In the early universe, dark matter began to clump in dense halos, creating gravitational wells into which normal baryonic matter fell. These halos provided the framework for gas to cool and condense into stars. As stars formed and gathered into galaxies, they traced the underlying dark matter distribution, weaving the cosmic web of filaments and voids we see on the largest scales. Simulations incorporating dark matter halos reproduce the observed large-scale structure of the universe with remarkable accuracy. Despite its central role, dark matter's true nature remains one of the greatest mysteries in science. Candidates range from WIMP's weakly interacting massive particles to Axions particles far lighter than electrons. To date, direct detection has eluded us, keeping dark matter at the frontier of both theoretical and experimental physics. Formation of stars following the threads woven by dark matter. In the universe's story, stars begin their lives within vast, cold clouds of gas and dust, molecular clouds, or nebulae composed, mostly, of hydrogen. Within these nebulae, regions of higher density can form, often triggered by dark matter's gravitational influence, nearby supernova shockwaves, or collisions between gas clouds. The cloud contracts, and its center becomes increasingly dense and hot, a process that can take millions of years but is crucial to star birth. During this collapse, a hot core called a protostar forms. As it continues to accumulate mass from the surrounding cloud, its temperature climbs. When the core reaches roughly 10 million degrees Celsius, hydrogen nuclei begin fusing into helium. This fusion releases tremendous energy, marking the birth of a true star. The onset of nuclear fusion halts further collapse by balancing the inward pull of gravity with the outward pressure of fusion. Energy, a delicate equilibrium that sustains a star for most of its life. The final size and mass of a star depend on how much material it can gather before fusion ignites. More massive stars, formed from denser or more extensive clouds, burn their nuclear fuel quickly and have shorter lifespans. Smaller stars, like our Sun, burn fuel more slowly and can shine steadily for billions of years. Stars rarely form in isolation. Within a single molecular cloud, many protostars may coalesce simultaneously, creating clusters of newborn stars. These stellar associations and open clusters remain gravitationally bound for some time before dispersing into the galaxy. The life cycle of a star is a journey spanning millions to billions of years. After the protostar phase, a star enters the main sequence, during which hydrogen fusion in its core produces helium and releases energy that counteracts gravity. For a star like the Sun, this phase lasts about 10 billion years. Once core hydrogen is exhausted, fusion ceases and the core contracts under gravity. The outer hydrogen shell ignites, causing the star's outer layers to expand and cool into a red giant. In this phase, a star can engulf close-orbiting planets and dramatically alter its system. For stars up to about 8 solar masses, the red giant eventually sheds its outer layers, creating a glowing planetary nebula. The core remains as a white dwarf and Earth's hot remnant that will cool and fade over billions of years. Massive stars, however, meet more violent ends. After fusing elements up to iron in successive shells, their cores collapse catastrophically, triggering supernova explosions that briefly outshine entire galaxies. These supernovae produce and disperse heavy elements throughout the cosmos. The collapsed core may form a neutron star, an ultra-dense object, a few kilometers across, or, if massive enough, a black hole whose gravity is so strong that not even light can escape. Within stars, nucleosynthesis transforms lighter elements into heavier ones. In more massive stars, helium and other light elements fuse into carbon, oxygen, silicon, and iron under extreme temperatures and pressures. Fusion of iron, however, consumes energy rather than releasing it, signaling the end of a massive star's life and leading to its supernova. In these explosive events, the universe's heaviest elements, gold, uranium, plutonium, are forged and expelled, enriching the interstellar medium. This cosmic recycling ensures that the elements essential for life are distributed throughout the galaxy, the iron in our blood, the calcium in our bones, and the oxygen we breathe all trace their origins to stellar furnaces and supernovas in the fiery hearts of stars long gone. A testament to the profound connection between the cosmos and every living thing within it, the universe stages a dramatic farewell when stars reach the end of their lives. What follows depends on the mass of the dying star. For stars like our Sun, the final act begins when all the hydrogen in the core has been fused into helium and the star expands into a red giant. This expansion is the star's attempt to find a new equilibrium as it starts fusing helium into heavier elements like carbon and oxygen in its core or in surrounding shells. Eventually, the star sheds its outer layers into space, creating a visually stunning planetary nebula and leaving behind a hot core that cools and dims over time, becoming a white dwarf. This dense, Earth-sized remnant will spend billions of years cooling and fading into the cosmic backdrop. Its nuclear fires extinguished, the fate of more massive stars is far more violent and spectacular. When these stars exhaust their nuclear fuel, they undergo a series of increasingly rapid and energetic fusion reactions, building a layered structure of elements with iron at the core. Because fusing iron does not release energy, the star can no longer counteract gravity's inward pull, leading to a catastrophic core collapse in a matter of seconds. This collapse triggers a supernova explosion, one of the most energetic events in the universe, which can briefly outshine entire galaxies and disperses elements forged within the star into space. The remnants of this explosion can become either a neutron star, an incredibly dense object only about 20 kilometers in diameter, but more massive than the Sun, or, if the progenitor was massive enough, a black hole, a point in space where gravity is so strong that not even light can escape. These end-of-life events are not merely spectacular cosmic fireworks. They play a crucial role in the universe's evolution. The elements produced and dispersed by dying stars seed the cosmos with the materials necessary for new stars, planets, and potentially life itself to form. Supernova, in particular, are responsible for creating and distributing heavy elements such as iron, calcium, and carbon across the galaxy. Delving into the cosmic ballet of galaxy formation, we embark on a journey spanning billions of years, in which the universe's fundamental forces choreograph the creation of these colossal celestial entities. Galaxies, vast islands of stars, gas, dust, and dark matter are the building blocks of the cosmos, and their formation is a tale woven by the laws of physics. In the beginning, following the Big Bang, the universe was a hot, dense sea of particles. As it expanded, temperatures dropped, allowing protons and electrons to combine into neutral hydrogen atoms. This era, known as recombination, marked the universe's transition from opacity to transparency, allowing light to travel freely for the first time. However, the universe was not perfectly uniform. Slight density variations, or ripples in the fabric of space-time left by the Big Bang, set the stage for galaxy formation. Gravity, the architect of the cosmos, amplified these tiny fluctuations. Regions slightly denser than their surroundings began to attract more and more matter, growing increasingly massive. This process, gravitational collapse, caused hydrogen gas clouds to condense, forming the first stars and protogalaxies, simple structures that would evolve into the complex galaxies we observe today. Galaxy formation, however, is not solely the product of gravity's inward pull. Other forces played pivotal roles, such as dark matter, a mysterious substance that does not emit, absorb, or reflect light, but exerts gravitational effects on visible matter, comprising about 85% of the universe's total matter. Dark matter acted as scaffolding for galaxy formation. It clumped together in the early universe, creating gravitational wells into which ordinary matter could fall and accelerating galaxy assembly. Feedback processes also significantly influenced galaxy evolution. Energy from star formation and supernova explosions heated and expelled gas from early galaxies, preventing it from cooling and collapsing too quickly. This self-regulation led to the diverse array of galaxy sizes and shapes observed today. From spiral galaxies like our Milky Way to elliptical and irregular galaxies, as galaxies grew, they did not evolve in isolation. Collisions and mergers were common, especially in the crowded early universe. These cosmic encounters could dramatically alter a galaxy's structure and star formation rate, creating morphological features such as spiral arms and seeding the growth of super black holes at their centers. Today, galaxies continue to evolve through interactions with their environment, including other galaxies and intergalactic gas. The study of galaxy formation and evolution sheds light on the universe's history and provides crucial insights into the fundamental processes governing the cosmos. It is a narrative of creation, transformation, and interaction, highlighting the intricate dance of matter and energy that shapes our universe. Galaxies come in a variety of magnificent forms, each with its own unique characteristics and origins, painting a rich tapestry of cosmic diversity. Among these, spiral, elliptical, and irregular galaxies stand out, each telling a different story of evolution and interaction. Spiral galaxies, such as our Milky Way, are distinguished by their flat disc-like appearance and swirling arms that emanate from a central bulge. This bulge is a dense concentration of older stars, while the arm sites of active star formation wrap around it in graceful arcs. Rich in gas and dust, these arms sparkle with bright nebulae and young hot stars. The spiral pattern itself is thought to result from density waves sweeping through the galaxy, compressing gas and dust and sparking star formation in a ripple effect. Elliptical galaxies, by contrast, lack the defined structure and spiral arms of their disc-shaped counterparts. They range from nearly spherical to elongated shapes and are composed mostly of older, redder stars, with minimal gas and dust, making them relatively barren in terms of new star formation. Their sizes also vary greatly, from giants that dominate local clusters to dwarfs that flit like shadows around larger neighbors. Many ellipticals are believed to form through the merging of smaller galaxies, a process that strips away gas and leaves behind a smoother, less structured remnant. Irregular galaxies, as their name suggests, lack the coherent structure seen in spiral and elliptical types. Chaotic in appearance, but rich in gas and dust, they are fertile grounds for star formation. Their distorted shapes often result from gravitational interactions or collisions with other galaxies, which can trigger bursts of new stars. Although they defy easy classification, irregular galaxies provide astronomers with valuable insights into the processes of galactic interaction and evolution. Beyond these broad categories lie subtypes and peculiar galaxies born of dynamic and sometimes violent interactions. Lenticular galaxies, for example, possess a large central bulge and a disk but lack spiral arms, placing them between spiral and elliptical forms. This diversity underscores the complexity of cosmic evolution and the influence of gravity, collisions, and mergers in shaping the universe's large-scale structure. The story of the Milky Way's formation is a cosmic saga spanning billions of years, weaving together gravity, dark matter, and the life cycles of stars. Central to this tale is hierarchical assembly, the process by which smaller components merge to form larger structures. Our barred spiral galaxy began its life about 13.6 billion years ago, not long after the Big Bang. In that early primordial soup of hydrogen, helium, and trace lithium. Slight density irregularities, perhaps influenced by dark matter coalesced under gravity into the first protogalaxies. As these protogalaxies orbited and merged, the nascent Milky Way grew in size and complexity. Dark matter, invisible yet detectable through its gravitational effects, guided the assembly of gas and stars into the galaxy's emerging structure. The Milky Way's disk, home to our solar system, formed gradually over billions of years as gas settled into the galactic plane and conserved its angular momentum. Successive generations of stars enriched the disk with heavier elements, synthesized in their cores, seeding the galaxy with the materials necessary for planets and life. At the galaxy's center lies the bulge, dense concentration of mostly old stars formed in its earliest stages, surrounded by a diffuse halo populated with globular clusters and the remnants of smaller galaxies the Milky Way has engulfed. The spiral arms, sites of ongoing star formation, arise from density waves compressing gas and dust, illuminating the disk with newborn stars through its history. The Milky Way has continued to grow via gas accretion and mergers with smaller galaxies. One significant future event will be its collision with the Andromeda Galaxy in about 4 billion years, a slow-motion encounter that will merge the two spirals into a single larger galaxy. Supermassive black holes occupy a pivotal role in this cosmic tapestry, acting as both anchors and architects of galactic evolution. Nestled at the centers of nearly every large galaxy, including our own E's, gravitational behemoths range from millions to billions of solar masses. Observations reveal a tight correlation between a galaxy's central black hole mass and the properties of its bulge, such as mass and velocity dispersion, suggesting a deep intrinsic link between black hole growth and galactic evolution. Supermassive black holes regulate star formation by accreting material and emitting vast amounts of radiation and outflows, which can heat or expel gas from the galaxy's core. This feedback limits the material available for new stars, ensuring galaxies do not exhaust their gas too quickly. In extreme cases, black hole activity can rayonize surrounding gas, preventing it from collapsing into stars. These processes shape galaxy size and structure, preventing runaway growth. Moreover, a supermassive black hole's immense gravity influences stellar orbits in the galactic center and can even eject high-velocity stars from the galaxy entirely. The formation and growth of these black holes likely begin with smaller seeds that grow through accretion of gas and dust and mergers with other black holes, processes that occur in tandem with their host galaxy's development, highlighting the interconnected evolution of galaxies and their central engines. Galaxies come in a variety of magnificent forms, each with its own unique characteristics and origins, painting a rich tapestry of cosmic diversity. Among these, spiral, elliptical, and irregular galaxies stand out, each telling a different story of evolution and interaction. Spiral galaxies, such as our Milky Way, are defined by their flat, disc-like shape and graceful swirling arms that emanate from a central bulge. This bulge is a dense concentration of older stars, while the arms, rich in gas and dust, are sites of ongoing star formation, often illuminated by bright nebulae and young hot stars. The spiral pattern itself is thought to arise from density waves that sweep through the disk, compressing gas and dust in a ripple effect that sparks new stars. Elliptical galaxies, by contrast, lack the defined structure and spiral arms of their disc-shaped cousins. They can range from nearly spherical to elongated shapes and are composed mostly of older, redder stars with very little gas or dust. As a result, new star formation is minimal, leaving ellipticals relatively quiescent. Their sizes vary widely. Some giants dominate local galaxy clusters, while dwarfs drift like faint shadows around larger neighbors. Many elliptical galaxies are believed to form through the merging of smaller galaxies, a process that strips away gas and smooths out irregularities. Irregular galaxies defy neat classification. Chaotic in appearance, they have no defined form but are often rich in gas and dust, making them fertile grounds for star formation. Their odd shapes usually result from gravitational interactions or collisions with other galaxies, which can trigger intense bursts of starbirth. Although irregulars appear disorderly, They provide valuable insights into the processes of galactic interaction and evolution. Beyond these main types, there are numerous subtypes and peculiar galaxies shaped by dynamic and sometimes violent encounters. Lenticular galaxies, for example, have a large central bulge and a disk, but no spiral arms, placing them between spirals and ellipses. This diversity underscores the profound influence of gravity, collisions, and mergers in sculpting the universe's large-scale structure. The Milky Way's formation is a cosmic saga, spanning some 13.6 billion years, almost as old as the universe itself. In the early cosmos, slight density irregularities, perhaps enhanced by dark matter, gathered into the first protogalaxies. These small systems merged repeatedly under gravity's pull, gradually building up the Milky Way's mass. Dark matter, invisible yet detectable via its gravitational effects, provided the scaffolding that guided gas and stars into the galaxy's growing structure. Over time, gas settled into a rotating disk, conserving angular momentum and giving rise to the spiral pattern we see today. Successive generations of stars forged heavier elements in their cores and dispersed them via stellar winds and supernova explosions, enriching the interstellar medium with the raw materials for planets and life. A dense central bulge, populated by many of the galaxy's oldest stars, and a diffuse halo studded with globular clusters bear witness to these ancient epochs. At the very heart of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass of about 4 million suns, surrounded by a bustling environment of stars, gas clouds, and magnetic filaments. SGRA** anchors the galaxy's dynamics. Its immense gravity influences nearby stars and gas, while occasional flares and high-energy emissions offer astronomers a unique laboratory for studying extreme physics. Observations in radio, infrared, and X-rays penetrate the thick veil of interstellar dust that otherwise obscures the galactic center in visible light. The Milky Way does not travel alone. It is orbited by a retinue of smaller satellite galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere. These dwarf companions engage in a gravitational dance with our galaxy, experiencing tidal stripping that pulls streams of stars and gas into vast arches. Over billions of years, some satellites are consumed entirely, leaving behind stellar streams that offer archaeological clues to the Milky Way's past mergers and growth. Looking ahead, the Milky Way faces a monumental future encounter, a predicted collision and eventual merger with the Andromeda Galaxy in about 4 billion years. This slow-motion cosmic dance will reshape both galaxies into a new, larger system. Throughout these grand processes, spiral arms forming, stars igniting, black holes feasting, and galaxies colliding. The Milky Way exemplifies the intricate interplay of matter, energy, and gravity that drives the evolution of the cosmos, currently in the process of being cannibalized by the Milky Way. This small galaxy is being torn apart by our galaxy's gravitational forces. The remnants of this ongoing merger, in the form of stellar streams wrapping around the Milky Way, are a testament to the dynamic nature of galactic evolution and the eventual fate of many satellite galaxies. These interactions are not merely incidents of cosmic violence, but fundamental processes that drive the evolution of galaxies. The accretion of satellite galaxies brings fresh gas into the Milky Way, fueling new generations of stars and contributing to the chemical complexity of our galaxy. At the same time, these mergers and interactions help to redistribute matter within the Milky Way, influencing its structure and dynamics. Peering into the future of the Milky Way galaxy unveils a narrative rich with cosmic evolution and dramatic transformations. As astronomers gaze through their telescopes and run simulations on powerful computers, they forecast a future in which the Milky Way undergoes significant changes shaped by the inexorable forces of gravity, the ongoing process of star formation, and impending galactic collisions. One of the most monumental events predicted to occur in the Milky Way's future is its collision with the Andromeda Galaxy. Currently, Andromeda, also a spiral galaxy like the Milky Way's about 2.5 million light-years away, but moving toward US at roughly 110 kilometers per second. In approximately 4 billion years, the skies above Earth, or any planet hosting observers at that time, will bear witness to this grand cosmic merger. As these two galaxies begin to intertwine, their mutual gravitational forces will draw them closer, eventually merging into a single, larger elliptical galaxy, sometimes humorously dubbed Milkomeda or Milkydromeda in scientific discussions. This merger is not expected to be a cataclysmic destruction of either galaxy, but rather a complex dance of stars and gas clouds. Given the vast distances between stars, direct collisions are unlikely. Instead, gravitational interactions will send stars and planetary systems into new orbits, possibly ejecting some from the newly formed galaxy altogether. The gas clouds within the galaxies, however, will collide. By the combined mass of the Milky Ways and Andromeda's supermassive black holes, these colossal black holes will gradually spiral toward each other and eventually merge. The future of the Milky Way, like that of all galaxies, will also be influenced by the life cycles of its stars. As stars exhaust their nuclear fuel, they will evolve through their life stages, with massive stars exploding as supernova and less massive stars shedding their outer layers to form planetary nebulae. Over trillions of years, this will leave behind a galaxy populated by dim white dwarfs, neutron stars, and black holes. Moreover, the universe's continuous expansion will have a profound effect on the Milky Way's future, making the universe appear increasingly empty from our vantage point. However, the gravitational bond between the Milky Way and its local group of galaxies will keep these cosmic neighbors together. The solar system and Earth reveal a captivating chapter in the story of the cosmos, showing how our sun, the planets, and the myriad smaller bodies that orbit our star came into being. Around 4.6 billion years ago, in a dark corner of the Milky Way, a vast cloud of gas and dust known as the solar nebula began to collapse under its own gravity. This collapse was likely triggered by the shock wave from a nearby supernova, which injected energy into the cloud and caused it to compress. As the nebula contracted, it started to spin and flattened into a rotating disk. With the densest material gathering at the center, through accretion, particles collided and stuck together, gradually forming a protostar at the heart of the disk. Material in the disk coalesced into increasingly larger bodies. Closer to the Sun, where temperatures were higher, Venus, Earth, and Mars rocky worlds composed mainly of silicate rocks and metals, with Earth alone harboring life as we know it. Further out, beyond the frost line where Esos could remain solid, gas giants and ice giants took shape. There, Jupiter and Saturn accreted massive envelopes of hydrogen and helium, while Uranus and Neptune accumulated their bulk from water, ammonia, and methane ices. In the outermost reaches of the solar system, the Kuiper Belt and the Oort cloud formed, becoming home to countless icy bodies, comets, largely unchanged since their formation, are relics of the early solar system. One of the most fascinating aspects of our system's evolution is Jupiter's role. Its immense gravity sculpted the orbits of other bodies, shaping the solar system's architecture and possibly ejecting some objects into the Sun or out into interstellar space. Over billions of years, the solar system has remained a dynamic environment, marked by collisions and migrations that have altered planetary orbits. Years ago, left craters on the Moon, Mercury, and Mars, serving as dramatic reminders of this tumultuous epoch. To unravel our system's formation, scientists combine observational data and provide insights into the formation of other planetary systems across the galaxy. The Milky Way itself played an indispensable role in our solar system's birth, set the stage for the solar nebula's collapse. The interstellar medium, primarily hydrogen and helium, with traces of dust and heavier elements from supernova. Within the galaxy's spiral arms, density waves compress the interstellar medium, triggering star formation. It was in such a region of a molecular cloud that the solar nebula coalesced. Moreover, the Milky Way's chemical composition shape, by its history of star formation and death, determined the types of planets that could form. Rocky inner planets emerged where high temperatures allowed only metals and silicates to condense. Relatively quiet region between the galaxy's major spiral arms shielded it from intense radiation and gravitational disturbances near the galactic center, fostering a stable environment conducive to life's development. Earth's own formation unfolded within this dynamic context. Material in the cooler outer disk regions stuck together to form planetesimals kilometer-scale building blocks of planets through ongoing accretion. These planetesimals merged into the rocky cores of the inner planets, including Earth. During its early growth, Earth endured intense bombardment. The energy released by these collisions, along with heating from radioactive decay, caused the young planet to partially melt, differentiating into a dense metallic core, a silicate mantle, and a lighter crust. Volcanic activity and outgassing released water vapor, carbon dioxide, methane, and ammonia into the atmosphere, filling surface basins to create the first oceans essential for life's chemistry. Earth's protective magnetic field, generated by its molten iron core. Over billions of years, photosynthetic organisms transformed the atmosphere by increasing oxygen levels and forming an ozone layer, paving the way for the rich biodiversity we observe today. In a few tens of millions of years, as Earth grew, its interior heated up due to the energy. It too differentiated into layers, a dense metallic core, a silicate mantle, and a crust on the surface. The formation of Earth's core was crucial for generating the planet's magnetic field, which protects the surface from harmful solar and cosmic radiation. Meanwhile, intense heat and volcanic activity released gases trapped in the rocks, contributing to the formation of Earth's early atmosphere. Water vapor, carbon dioxide, methane, and ammonia were among the gases released, creating a primordial atmosphere very different from the one we breathe today as Earth continued to cool. Water vapor in the atmosphere condensed and fell as rain, filling basins on the planet's surface and creating the oceans. The presence of liquid water essential for lifelong, with the stability provided by Earth's size, orbit, and protective magnetic field, set the stage for life's eventual emergence. Over billions of years, Earth's atmosphere and surface evolved. Photosynthetic organisms transformed the atmosphere by increasing its oxygen content and making it hospitable to a diverse range of life forms, life-supporting planet we know today. The emergence of life on Earth, a planet teeming with diverse organisms, resulted from a unique combination of conditions and events unfolding over billions of years. One of the most fundamental factors was Earth's position in the solar system's Goldilocks zone or habitable zone, where it is neither too close to the sun, which would make liquid water impossible, nor too far away, which would make it too cold. This orbit allowed liquid water to persist on the surface, a critical ingredient for life. The formation of Earth's atmosphere was another crucial step. Initially composed of volcanic gases such as water vapor, carbon dioxide, and ammonia, the atmosphere underwent significant changes over time. The rise of photosynthetic organisms capable of converting life forms, but also formed the ozone layer, which protects the surface from harmful ultraviolet radiation. Earth's magnetic field, generated by the movement of molten iron in its outer core, shields the planet from solar and cosmic radiation that could strip away the atmosphere and harm living organisms. This protective field ensures that the atmosphere remains intact and provides a stable environment for life. Moreover, Earth's geological activity has played a significant role in creating conditions favorable for life. Plate tectonics. The movement of the planet's lithospheric plates has led to the formation of continents and ocean basins, the recycling of carbon through the carbon-silicate cycle, and the regulation of global temperature. This dynamic geological activity has also facilitated the distribution of minerals and nutrients essential for life, creating diverse habitats and environments. The presence of water in all three, solid, liquid, and gas on Earth's surface, is another condition pivotal to life. Water acts as a solvent, facilitating the chemical reactions necessary for life, and its unique properties, such as its ability to dissolve a wide range of substances, have been crucial to the development of complex biological molecules. Lastly, Earth's natural satellite, the Moon, has contributed to the stability of the planet's climate by stabilizing its axial tilt, which influences seasonal variations. The relatively mild and stable climate resulting from this axial tilt has allowed a wide range of ecosystems to flourish over millions of years. Advanced topics. Dark energy, a term evoking mystery and intrigue, plays a pivotal role in the cosmos, fundamentally influencing the universe's fate and structure. This enigmatic force, which makes up about 68% of the universe, is responsible for its accelerated expansion. a discovery that reshaped cosmology when first observed in the late 1990s. The concept of dark energy emerged from observations of distant supernova, which showed that galaxies are moving away from each other at an accelerating rate contrary to the expectation that gravity would slow the expansion. This acceleration suggested an unknown form of energy permeating all of space, exerting a repulsive force that overcomes gravity on cosmological scales. Dark energy's true nature remains one of physics' greatest mysteries, but its effect on cosmic expansion is clear. By accelerating expansion, it impacts the formation and evolution of galaxies. Without dark energy, the universe might have collapsed under its own gravity or expanded far more slowly, leading to a very different cosmic landscape. One leading theory for dark energy is the cosmological constant, introduced by Albert Einstein as a modification to general relativity. In this view, dark energy represents a constant energy density filling space. Another possibility is that dark energy is a dynamic field, similar to the electromagnetic field, with properties that vary across space and time, potentially changing the universe's fate. If dark energy's density remains constant or increases, the universe could expand indefinitely, growing colder and emptier as galaxies drift apart, a scenario known as the Big Freeze or heat death. Alternatively, if dark energy strengthens over time, it could tear apart galaxies, stars, planets, and even atoms in a big rip. Understanding dark energy is crucial, not only for cosmology, but also for fundamental physics, as it challenges existing theories and may point to new laws of nature. Scientists are actively researching dark energy through observations of the cosmic microwave background, galaxy distributions, and supernova, as well as experiments designed to probe the nature of space and energy. Galaxies, the vast assemblies of stars, gas, dust, and dark matter that populate the universe, are not static entities, but are constantly evolving. This evolution unfolds over billions of years, driven by a variety of cosmic forces and phenomena. Understanding how galaxies evolve is key to unlocking the cosmos's secrets, revealing the life cycle of its fundamental building blocks. The evolution of galaxies depends on their initial mass, the environment in which they reside, and their interactions with other galaxies and intergalactic matter. In the early universe, shortly after the Big Bang, galaxies began as small protogalaxies that grew over time through the accretion of gas and mergers with other protogalaxies. These processes produced the diversity of galaxy shapes and sizes we observe today, from spiral galaxies like the Milky Way to ellipticals and irregulars. In spiral galaxies, star formation plays a crucial role in their evolution. They're arms-rich in gas and dust star sites of active star formation, where new stars are born from the gravitational collapse of gas clouds. Over time, as these galaxies exhaust or lose their interstellar gas through star formation or supernova-driven ejections, their star formation rates decline and their stellar populations age. Older, redder stars then dominate their appearance. Elliptical galaxies, by contrast, often result from mergers of smaller galaxies. These dramatic events can trigger bursts of star formation as gas clouds collide and collapse, but they also scatter and heat gas, making future star formation less likely. Consequently, ellipticals typically contain older, redder stars and have less interstellar gas available for new stars than spirals. Galaxy interactions, mergers, and close encounters are another significant driver of galactic evolution. When two similarly sized galaxies merge, they can form a larger elliptical, disrupting spiral structures and igniting a short-lived but intense starburst. Gravitational encounters with neighboring galaxies can also distort a galaxy's shape, producing tidal tails or bridges. Internal processes further shape galactic evolution. Supernova inject energy into the interstellar medium, heating and expelling gas, which can inhibit additional star formation. Active galactic nuclei, aged and powered by material accreting onto central supermassive black holes, can likewise expel vast amounts of gas from their host galaxies, further regulating star formation activity. As galaxies age, their star formation rates generally decline, leading to an older, redder stellar population. This aging process is influenced by environment, galaxies in dense regions, such as cluster centers, often evolve more rapidly due to frequent interactions and gas stripping by the hot intracluster medium, galaxy collisions. Colossal events unfolding over hundreds of millions of years play a pivotal role in cosmic evolution. Despite the vast distances between individual stars, gravitational forces during collisions redistribute gas, dust, and stars, creating intricate structures such as tidal tails, rings, and bridges. One of the most significant outcomes of these collisions is the triggering of starburst events. As galaxies merge, their gas clouds compress, spawning regions of intense star formation that can produce millions of new stars in a relatively short time. These starbursts reshape galaxies' appearances and drive the synthesis of heavier elements in stellar cores. Collisions can also bring supermassive black holes together. As galaxies merge, their central black holes spiral inward and eventually coalesce, releasing enormous energy and influencing surrounding galactic dynamics, including further regulating star formation. Moreover, many astronomers believe that mergers between spiral galaxies produce elliptical galaxies. Such unions mix stars and gas, smoothing out previous spiral structures into more uniform ellipsoidal shapes. On larger scales, galaxy collisions and mergers form the foundation of the hierarchical model of galaxy formation, which describes how galaxies assemble and evolve through the accumulation of smaller systems. This process, ongoing since the early universe, continues to shape the large-scale structure of the cosmos, influencing the distribution and evolution of galaxies within clusters and superclusters. The significance of galaxy collisions extends beyond immediate structural changes. They stand as testament to the universe's dynamic nature, offering astronomers critical insights into cosmic evolution, dark matter behavior, and the gravitational forces that govern galaxies. Observations and simulations of these encounters not only reveal the past and present of the universe, but also hint at its future. Our own Milky Way is on a collision course with the Andromeda Galaxy, promising a spectacular merger in about 4 billion years. Predicting the universe's future lies at the heart of cosmology, combining observations, theoretical physics, and simulations to peer into cosmic time. Although absolute certainty remains elusive due to the complexities and unknowns of cosmic physics, scientists have developed several scenarios based on current understanding of fundamental laws: dark energy, dark matter, and gravity. Factor in these predictions is dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy continues to dominate the cosmic energy budget, the universe will likely expand indefinitely. In this big freeze, or heat death scenario, galaxies recede ever faster. Star formation ceases as gas is depleted, and the universe cools as it expands. Over trillions of years, existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Eventually, even these remnants may decay or be swallowed by black holes, rendering the universe a cold, dark, and empty expanse. With black holes themselves evaporating through Hawking radiation over vast timescales, another possibility hinges on dark energy's nature. If it strengthens over time, the universe could end in a big rip, where galaxies, stars, planets, and even atoms are torn apart by accelerating expansion. If dark energy changes over time, growing stronger, it could lead to a big rip. In this scenario, dark energy's repulsive force would eventually overcome all other forces, tearing galaxies, stars, planets, and even atoms apart and bringing the universe to a cataclysmic finale. Alternatively, if the universe contains enough matter, including dark matter, to counteract the expansion driven by dark energy, its expansion could reverse in a big crunch. In that case, the universe would collapse back on itself in a mirror image of the Big Bang, potentially seeding a new universe in an endless cycle. A related idea, the Big Bounce, suggests that the universe could cyclically expand and contract. According to this theory, our current expansion phase might one day reverse into a big crunch, which would then trigger another Big Bang, and the cycle would repeat. Though tied to quantum gravity concepts, this remains speculative and awaits further evidence and theoretical development. Predicting the universe's future also requires understanding the fates of its structures. Galaxies will continue evolving. Stars will exhaust their nuclear fuel, and black holes may come to dominate the cosmic landscape before gradually evaporating via Hawking radiation over vast timescales. While these scenarios outline possible futures based on our present understanding of cosmology, they may evolve as we learn more particularly about dark energy and dark matter. Nonetheless, these forecasts underscore the dynamic, ever-changing, the nature of the cosmos, and illuminate the profound questions driving modern cosmology. Astronomers employ an array of sophisticated techniques to observe distant galaxies and stars, unraveling the cosmos's mysteries. At the heart of these endeavors are telescopes, colossal instruments, equipped with cutting-edge technology, stationed around the globe and even beyond Earth's atmosphere to capture the faintest whispers of light from billions of light years. Away, the light we see from these distant celestial bodies is not merely illumination. It carries the universe's secrets. By analyzing this light, scientists can determine a star or galaxy's composition, distance, age, and velocity in the cosmic dance. Spectroscopy, a technique that breaks light into its component wavelengths, makes this possible. Much like a prism turning sunlight into a rainbow, a spectrograph reveals characteristic spectral lines for each element. Studying those lines tells astronomers which elements are present. While shifts toward the red or blue ends of the spectrum, the redshift and blue shift indicate whether an object is moving away from or toward us, and at what speed. Rooted in the Doppler effect, this phenomenon led to the groundbreaking discovery of the expanding universe. A pillar of modern cosmology. Technological advancements have further expanded our cosmic horizons. The Hubble Space Telescope has returned images of unprecedented clarity, revealing intricate structures in distant galaxies and nebulae. Its successor, the James Webb Space Telescope, aims to peer even deeper, observing the first galaxies that formed after the Big Bang by operating above Earth's atmosphere. These space-based observatories evade atmospheric distortions, delivering sharper, more detailed views. In tandem with optical telescopes, radio telescopes listen to the universe's whispers at longer wavelengths. Giant dishes capture radio waves emitted by celestial objects, offering a different perspective on the cosmos. For instance, they detect the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang, providing critical insights into the universe's earliest moments. Integrating observations across the entire electromagnetic spectrum from radio waves to gamma rays gives a more complete picture of the universe. This multi-wavelength astronomy has led to the discovery of exotic phenomena such as quasars and pulsars, further enriching our understanding of cosmic evolution. Building on the foundations of telescopes and spectroscopy, a myriad of technologies plays pivotal roles in galactic studies. Among these, adaptive optics stands out as a game-changer for ground-based astronomy. By using a reference store, an artificial laser guide start to measure atmospheric distortion in real time. Adaptive optic systems adjust to telescopes' mirrors to counteract the blurring effects of Earth's atmosphere, allowing ground-based observatories to achieve near-space quality resolution. Interferometry is another critical technology. By combining light collected by multiple telescopes, interferometry creates a virtual telescope as large as the distance between them. The Very Large Telescope (VLT) in Chile and the Atacama Large Submillimeter Array (ALMA) are prime examples, enabling scientists to study star birth, planetary system formation, and the intricate structures of galaxies far beyond our own. With unprecedented clarity, radio astronomy remains a cornerstone of our quest to understand the galaxy. Unlike optical telescopes, which capture visible light, radio telescopes detect radio waves from celestial sources, revealing otherwise invisible phenomena such as fast radio bursts and the cosmic microwave background. The Square Kilometer Array (SKA), an international effort to build the world's largest radio telescope, promises to revolutionize our understanding of the universe from its early epochs to the large scale distribution of galaxies. Space missions and satellites also play indispensable roles. The Gaia Observatory is mapping the positions and motions of billions of stars in the Milky Way, providing essential data for understanding our galaxy's structure, formation, and evolution. Meanwhile, Missions like Kepler and TESS transiting exoplanets survey satellites scour the galaxy for exoplanet worlds, orbiting stars beyond our solar system, offering tantalizing insights into the potential for life elsewhere in the cosmos. Venturing into the vast expanse of the universe. Astronomers employ a suite of sophisticated techniques to observe distant stars and galaxies, gradually unraveling the cosmos's mysteries. Central to these efforts are telescopes, colossal instruments, outfitted with cutting-edge technology deployed both around the globe and beyond Earth's atmosphere to capture the faintest whispers of light from billions of light years. Away, that light is far more than a mere glow. It is a messenger carrying the universe's secrets. By analyzing it, scientists can determine an object's chemical composition, distance, age, and even its velocity in the cosmic dance. Spectroscopy, breaking light into its component wavelengths, is the key. Like a prism transforming sunlight into a rainbow, a spectrograph reveals characteristic spectral lines for each element. Shifts toward the red or blue ends of the spectrum, redshift or blue shift, indicate motion away from or toward us respectively, and at what speed. This Doppler effect phenomenon led to the pivotal discovery that the universe is expanding, laying the foundation for modern cosmology. Technological advances have vastly expanded our view. The Hubble Space Telescope has returned images of unprecedented clarity, unveiling intricate structures in distant galaxies and nebulae. Its successor, the James Webb Space Telescope, peers even deeper, targeting the first galaxies that formed after the Big Bang. By operating above Earth's atmosphere, these observatories avoid atmospheric distortion and deliver sharper, more detailed observations. In parallel, radio telescopes listen to the universe at longer wavelengths. Giant dishes capture radio waves emitted by celestial objects, offering a complementary perspective. They detect signals such as the cosmic microwave background, the afterglow of the Big Bang, providing critical insights into the universe's infancy. Integrating observations across the entire electromagnetic spectrum, from radio waves to gamma rays, GIVs, the most complete picture of the cosmos. Multi-wavelength astronomy has revealed exotic phenomena like quasars and pulsars, enriching our understanding of cosmic evolution beyond telescopes and spectroscopy. A host of advanced technologies enhances our observational power. Adaptive optics, for example, corrects in real time for Earth's atmospheric turbulence. By using a natural or laser guide star to measure atmospheric distortion, adaptive optics systems adjust a telescope's mirrors, producing sharp, near-space quality images from the ground. Interferometry takes resolution even further by combining light from multiple telescopes into one virtual instrument, the size of the separation between them. Facilities like the Very Large Telescope VLT in Chile and the Atacama Large Millimeter Submillimeter Array ALMA exploit this technique to study star formation, planetary system birth, and galaxy structure with unprecedented clarity. Radio astronomy remains indispensable. It reveals phenomena invisible at optical wavelengths, such as fast radio bursts and the faint glow of the cosmic microwave background. The upcoming Square Kilometer Array, SKA, promises to revolutionize our understanding of the universe from its earliest epochs to the large scale. The Gaia Observatory is mapping the positions and motions of billions of Milky Way stars, essential for charting our galaxy's structure, formation, and evolution. Meanwhile, missions like Kepler and TESS scour the sky for exoplanets, worlds orbiting distant stars, offering tantalizing clues about the prevalence of potentially habitable environments elsewhere. Finally, together, the massive datasets generated by modern observatories are sifted and interpreted through sophisticated computer models and simulations. These tools allow scientists to test theories of galaxy formation, black hole behavior, and the universe's evolution in ways once unimaginable, ushering in a new era of discovery. Theoretical astrophysics provides the scaffolding upon which our understanding of the universe is built, offering profound insights that stretch beyond the reach of current observations. These models, grounded in mathematics and physics, bridge the concrete world of data and the abstract realm of what could be, enabling scientists to predict phenomena yet unseen and explain those already observed. At their core lie principles that govern everything from the smallest particles to the largest cosmic structures. One of the cornerstones of modern theoretical physics is the Standard Model of particle physics, which describes the fundamental particles and forces that constitute the universe. This framework famously predicted the existence of the Higgs boson discovered in 2012, providing evidence for the mechanism by which particles acquire mass. Its discovery was a triumph for theoretical models guiding experimental research in the cosmic arena. Einstein's theory of general relativity revolutionized our understanding of gravity, curvature of spacetime caused by mass and energy. General relativity predicted phenomena such as gravitational lensing, Mercury's orbital precession, and the existence of black holes, each later confirmed by observation. The theory also laid the groundwork for understanding cosmic expansion and for predicting gravitational waves, which were detected a century after Einstein's original proposal. To explain the universe's large-scale structure and evolution, cosmologists rely on the CDM model, which incorporates dark matter and dark energy. Numerical simulations based on this model recreate the universe's evolution from shortly after the Big Bang to its current state, illuminating how galaxies cluster and how vast cosmic webs form. These simulations, by adjusting parameters such as dark matter density or star formation rates, reveal the sensitivity of cosmic evolution to underlying physics. Theoretical models also address phenomena beyond current observational reach. Cosmic inflation theory, for instance, posits a period of exponential expansion in the early universe, resolving puzzles like the uniformity of the cosmic microwave background. Although direct evidence for inflation remains elusive, its framework aligns with observations and guides the search for new empirical data. The interplay between theory and observation is dynamic and iterative. Models predict phenomena that drive experimental design, while unexpected observations challenge existing theories, prompting their refinement or replacement. This symbiosis fuels progress in cosmology, sharpening our understanding of the universe. Simulations in astrophysics act as digital cosmoses, allowing scientists to explore the universe's intricacies where physical experiments cannot. By inputting physical laws and initial conditions into sophisticated computer programs, researchers watch cosmic events unfold in virtual universes. These simulations handle the vast scales of space and time inherent in astrophysical phenomena such as galaxy formation, which involves gravity, gas dynamics, star formation, and feedback from supernova and supermassive black holes over billions of years. Simulation-based studies of the cosmic web, a vast network of dark matter filaments hosting galaxies and clusters, compare virtual structures to telescope surveys, refining our understanding of dark matter's role. In planetary science, models explore planet formation, atmospheric chemistry, and potential biosignatures, informing the design of missions to detect Earth-like worlds. Simulations also illuminate cataclysmic events, supernova, black hole mergers, and galaxy collisions, predicting gravitational wave signatures, elemental abundances, and merger dynamics that observations can test. In this way, virtual universes become laboratories for theories that cannot be directly experimented upon, offering insights into the cosmos's past, present, and future, and deepening our connection to the universe we seek to understand. Simulations in astrophysics model dark matter, gas, stars, and other components of the universe by solving equations derived from gravity, thermodynamics, and hydrodynamics. By adjusting the initial conditions and physical laws in these simulations, scientists can explore how different factors influence galaxy formation and then compare the results with telescope observations to test their model's accuracy. Element in these simulations is dark matter, invisible substance that neither emits nor absorbs light but exerts gravitational force on visible matter, constituting about 85% of the universe's total matter. Dark matter provides the gravitational scaffolding around which galaxies form. In practice, simulations initialize dark matter distributions based on cosmic microwave background observations, the afterglow of the Big Bang, which reveals matter's arrangement just 380,000 years after the universe began. As simulated, time advances. Dark matter clumps under gravity to form dense regions called halos. Gas then falls into these halos, cools, and condenses to create stars and galaxies, to capture the full complexity of galaxy formation. Simulations also include feedback processes from stars, such as supernova explosions and stellar winds, can eject gas from galaxies and regulate further star formation. As new astronomical observations yield data on galaxies at various epochs, these models are continually refined. Observing distant galaxies allows scientists to look back billions of years in time, providing critical tests for the accuracy of their simulations. You've found a place to rest your mind. Welcome to Space Mirage. In this episode, we're exploring how the universe was born from pure nothingness, softly and slowly. So lie down, plug in your earphones, close your eyes, and let science help you drift off. How did everything start from nothing? It's a deep philosophical mystery that makes us think about the very nature of existence and how the universe came to be. Universe appeared, bringing with it the particles that would form everything we see around us. This question goes beyond scientific inquiry, touching on what it means to exist, what nothingness is. This documentary, we explore these questions by looking at the universe through the eyes of particle physics and cosmology. Scientists use math and experiments to try to answer these big questions. But underneath their research lies a deeper question. What does it mean for something to come from nothing? How can the laws of physics explain the emergence of the universe from a state where there was no space, no time, and no matter? Particle physics is a branch of science that delves into the world of the very small, exploring the fundamental particles that make up the universe and the forces with which they interact. Unlike the familiar objects of our daily lives, the subatomic realm operates under the rules of quantum mechanics, revealing a world that is both fascinating and counterintuitive. Physics is the quest to understand what the universe is made of and how it works. At the most basic level, scientists in this field study particles like quarks, electrons, and neutrinos, which are the building blocks of atoms themselves. Blocks of matter? These particles are incredibly small. Physics has been the development of the Standard Model, a theory that describes the fundamental forces except for gravity and particles that constitute the universe. According to the Standard Model, there are four fundamental forces: the electromagnetic force, which causes electric and magnetic effects; the weak nuclear force, which plays a role in radioactive decay; the strong nuclear force, which binds quarks together in the nucleus of an atom. Of particles in countless experiments, yet it is not the final word. Scientists are still searching for a more complete theory that can include gravity and account for the mysteries of dark matter and dark energy, which make up most of the universe's mass and energy, but remain elusive to direct detection. Research in particle physics requires incredibly sophisticated technology, such as particle accelerators and detectors. These machines accelerate particles to nearly the speed of light and then collide them, allowing researchers to observe the resulting interactions and particles that are produced. Is one of the most powerful particle accelerators in the world. It was here that the Higgs boson, a particle predicted by the Standard Model that gives other particles mass, was discovered in 2012. This discovery was a monumental step forward, filling a crucial gap in our understanding of particle physics. Despite its complexities, the field of particle physics is driven by a simple and profound question. What is the universe made of? The pursuit of an answer has led to groundbreaking discoveries and technologies, including the World Wide Web, which was initially developed at CERN, the European Organization for Nuclear Research, to facilitate information sharing among scientists. As we delve deeper into the mysteries of the universe, cosmology, the study of the universe's origins, structure, and evolution, finds a surprising partner in particle physics. With its focus on the fundamental constituents of matter and the forces that govern their interactions, this synergy opens up new pathways to understanding not just what the universe is made of, but also how it began and has evolved over billions of years. At the core of this intersection is the Big Bang Theory, a cornerstone of cosmology that posits the universe started from an incredibly hot, dense state approximately 13.8 billion years ago and has been expanding ever since. Particle physics enhances our understanding of this primordial moment by examining the behavior of particles at extremely high energies, similar to those that would have existed just fractions of a second after the Big Bang. For instance, the Conditions of the early universe are recreated on a miniature scale within the colossal particle accelerators like the Large Hadron Collider, allowing scientists to study reactions that, while dark matter is thought to be made of particles that do not absorb, reflect, or emit light, making them invisible and detectable only through their gravitational effects. Dark energy is believed to be responsible for the accelerated expansion of the universe. Particle physicists are on the hunt for particles that could constitute dark matter, using both underground detectors and space-based observatories to search for signs of these elusive particles, while cosmologists incorporate these findings into their models of the universe's overall structure and dynamics. Furthermore, the study of cosmic microwave background radiation, a relic of the Big Bang, offers a compelling example of how cosmology and particle physics intersect. This radiation provides a snapshot of the universe when it was just 380,000 years old, before stars and galaxies had formed. By analyzing its subtle temperature variations, scientists gain insights into the distribution of matter and the nature of the universe's early conditions, informing theories in both cosmology and particle physics about the fundamental forces and particles at play during the universe's formation. This interdisciplinary approach not only broadens our understanding of the universe, but also challenges and refines the theories in both fields. For example, discrepancies in measurements of the Hubble constant, which describes the rate at which the universe is expanding, the prevailing cosmological model. Such anomalies drive the quest for a more unified theory that can reconcile the laws governing the cosmos on the largest scales with those ruling the smallest. Particles, building on the exploration of how cosmology intersects with particle physics, it's essential to delve into the fundamental forces of nature, which are the backbone of both the cosmos at large and the world of subatomic particles. These forces are like the universe's rulebook, dictating how everything from galaxies to quarks interacts. Understanding these forces provides insights into everything from the movement of planets to the stability of matter itself. There are 4 recognized fundamental forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each plays a crucial role in the universe's structure and dynamics, influencing interactions at different scales and energies. Gravity is perhaps the most familiar force. It's the force that keeps our feet on the ground and governs the motion of planets, stars, and galaxies. Despite its universal presence, gravity is the weakest of the 4 forces. However, its influence spans immense distances, holding the universe. Together, the force of gravity between 2 objects is determined by their masses and the distance between them, as described by Isaac Newton's law of universal gravitation. Albert Einstein's theory of general relativity later refined our understanding of gravity, describing it as the curvature of space-time around masses. Electromagnetism is the force responsible for almost all the phenomena encountered in daily life above the nuclear scale. It acts between charged particles, such as protons and electrons, and is the force behind electricity, magnetism, and light. Electromagnetism is far stronger than gravity at the particle level and is essential for the structure of atoms, the chemical bonds between atoms, and the transmission of signals within our bodies. The strong nuclear force, also known as the strong interaction, is the strongest of the 4 forces, but acts over a very short range. It binds protons and neutrons together in the nucleus of an atom. Without the strong force, atoms would not exist in their current form. As it overcomes the electromagnetic repulsion between positively charged protons within the nucleus and neutrons, the components of atomic nuclei, the weak nuclear force. It acts over an even shorter range than the strong force and is pivotal in processes that change one type of subatomic particle into another, such as the transformation of a neutron into a proton, electron, and neutrino. This force plays a crucial role in the nuclear fusion reactions that fuel stars and, by extension, the synthesis of elements throughout the universe. These fundamental forces of nature are integral to the theories and experiments that bridge the vastness of cosmology with the intricacies of particle physics. Scientists strive to develop a unified theory that can cohesively explain all 4 forces within a single framework, a goal that has remained elusive. The quest for such a theory, often referred to as the theory of everything, continues to drive much of the research in physics promising to unlock further mysteries of the universe. Let's delve into the particles that are considered the very building blocks of matter itself. These particles form the foundation of everything visible and tangible in our world, from the air we breathe to the stars in the night sky. The standard model of particle physics provides a framework that identifies the smallest constituents of matter, categorizing them into quarks, leptons, and the force carrier particles that mediate the fundamental forces. Quarks are incredibly tiny particles that combine to form protons and neutrons, the components of atomic nuclei. There are 6 types, or flavors of quarks: up, down, charm, strange, top, and bottom. Quarks are never found in isolation in nature due to a phenomenon known as color confinement. They are always bound together in groups of 2 or 3, forming particles known as mesons and baryons, respectively. Protons are made up of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. The properties and interactions of quarks are determined by the strong nuclear force, the most powerful of the 4 fundamental forces, which keeps them locked together within the nucleus. Leptons are another category of fundamental particles, with the electron being the most well-known member. Like quarks, there are 6 flavors of leptons: the electron muon tau and their corresponding neutrinos, electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, leptons do not experience the strong nuclear force. Electrons orbit the nucleus of an atom, playing a crucial role in chemical reactions and electrical conductivity. Neutrinos are elusive particles that barely interact with matter, making them incredibly difficult to detect, despite being produced in vast quantities by the sun and other nuclear processes. In addition to quarks and leptons, the standard model includes force carrier particles, known as bosons, which mediate the 4 fundamental forces. Photons carry the electromagnetic force. Gluons mediate the strong force. W and Z bosons are responsible for the weak force, and the recently confirmed Higgs boson is associated with the Higgs field, which gives particles their mass. As we continue our journey, we venture into the realm of the Big Bang Theory, a pivotal concept that provides a compelling explanation for the origin of the universe. This theory is a cornerstone of modern cosmology and offers a window into the universe's earliest moments, suggesting that everything we observe today, dense and hot point, approximately 13.8 billion years ago. The Big Bang Theory proposes that the universe was once in an extremely hot and dense state that expanded rapidly. This expansion is not like an explosion of matter moving outward to fill an empty space, but rather the expansion of space itself. Imagine a balloon with dots on it representing galaxies, illustrating how galaxies move apart as the universe expands. Evidence supporting the Big Bang Theory is multifold and compelling. One of the key pieces of evidence is the cosmic microwave background radiation, CMB, a faint glow that permeates the universe, discovered accidentally by stretched to microwave frequencies by the expansion of the universe. Observations of the CMB provide a snapshot of the infant universe, allowing scientists to glean insights into its early conditions and composition. Another cornerstone of evidence comes from the observation of the redshift of galaxies, indicating that the universe is still expanding. This redshift occurs because the light from distant galaxies is stretched to longer, redder wavelengths as the space between us and the galaxies expands. Edwin Hubble was the first to observe this phenomenon in 1929, providing direct evidence that the universe is not static but dynamic and ever-expanding. Furthermore, in the universe, hydrogen, helium, and lithium observed today. These elements were formed during the first few minutes after the Big Bang in a process known as nucleosynthesis, and their proportions align closely with the predictions. Supporting it, the Big Bang Theory is not without its unanswered questions and mysteries, such as the nature of dark matter and dark energy, which dominate the universe's total mass-energy content, yet remain elusive. Moreover, the theory does not explain what preceded the Big Bang or the underlying cause of the initial expansion, leaving room for further theoretical and observational exploration. The Big Bang Theory has revolutionized our understanding of the universe's origins, structure, and evolution. It paints a picture of a dynamic universe, born from a singular state of unimaginable density and heat, evolving over billions of years into the complex cosmos we observe today, In the immediate aftermath of the Big Bang, the universe was a hot, dense sea of energy. Conditions were so extreme that matter as we understand, its atoms, molecules, and their constituents, could not yet exist. Instead, the universe was filled with a quark-gluon plasma, a state in which quarks, the building blocks of protons and neutrons, and gluons, the particles responsible for the strong force that binds quarks together, moved freely in an ultra-hot, dense environment. This phase is akin to a soup of the universe's most fundamental ingredients, simmering in the aftermath of its explosive birth. As the universe expanded, it began to cool. Within the first microseconds, it cooled sufficiently for quarks to start binding together, forming protons and neutrons, the nuclei of future atoms. This period, known as the Hadron Epoch, marked the universe's first step toward the formation of matter as we recognize it. Further cooling allowed protons and neutrons to begin forming the universe's first nuclei. During the nucleosynthesis phase is a single proton, deuterium, a stable isotope of hydrogen with one neutron, helium, and trace amounts of lithium. The precise ratios of these light elements, predicted by the Big Bang nucleosynthesis theory, match closely with what we observe in the universe today, providing strong support for the Big Bang model. However, the universe remained too hot for electrons to bind to these nuclei to form neutral atoms. It wasn't until approximately 380,000 years after the Big Bang, during a period known as recombination, that the universe had cooled enough for electrons to combine with nuclei, creating the first neutral atoms. This event dramatically changed the universe's structure, allowing light to travel freely through space for the first time, leading to the release of the cosmic microwave background radiation, a snapshot of the infant universe that provides critical evidence for the Big Bang. The formation of the first neutral atoms marked the universe's transition from a plasma state to one that could eventually support stars, galaxies, and planets. Gravity began to pull matter together, leading to the formation of gas clouds that would become the nurseries for the first stars. These first stars synthesized heavier elements in their cores, contributing to the rich chemical diversity we observe. In the universe today, the evidence for the Big Bang theory not only corroborates the notion that the universe originated from a singular, extremely dense and hot state, but also offers insights into the dynamics of the cosmos over billions of years. This evidence is crucial for both the scientific community and the broader public, offering a coherent narrative of cosmic evolution that is grounded in observation and analysis. The cosmic microwave background radiation, Robert Wilson, the CMB, is a faint glow of light that fills the universe, remaining from the time shortly after the Big Bang. This radiation is the afterglow of the universe's infancy, cooled to microwave frequencies by the expansion of the universe. Over billions of years, measurements of the CMB by satellites such as COBE, WMAP, and Planck have provided a detailed picture of the early universe, showing slight temperature fluctuations that correspond to regions of slightly different densities. These fluctuations were the seeds of all future structure, the galaxies, stars, and planets that fill the universe today. The expansion of the universe itself serves as direct evidence for the Big Bang. In the 1920s, with their speed proportional to their distance from us. This observation, known as Hubble's law, suggests that the universe is expanding uniformly, implying that it was once far smaller, hotter, and denser. As the Big Bang theory predicts, the expansion of the universe is a dynamic testament to its explosive origin. The abundance of light elements provides another key piece of evidence. The Big Bang theory predicts the production of hydrogen, helium, and traces of lithium during the first few minutes after the Big Bang in a process known as primordial nucleosynthesis. Observations of the relative amounts of these elements in the universe closely match the predictions made by the Big Bang model, supporting the theory that the universe was once in a hot, dense state conducive to the formation of these elements. The large-scale structure of the universe, as observed through the distribution of galaxies and galaxy clusters, supports the Big Bang theory. Galaxies are not randomly distributed throughout the universe, but instead form a vast web of filaments and voids. This structure is consistent with the gravitational growth of initially small fluctuations in the density of the early universe predicted. By the Big Bang Theory, continuing on our journey, we delve into the concept of quantum fluctuations, a phenomenon deeply rooted in the quantum realm that plays a pivotal role in the fabric of the cosmos. Quantum fluctuations are temporary changes in the amount of energy in a point in space, as dictated by Werner Heisenberg's uncertainty principle, which states that certain pairs of physical properties like position and momentum cannot both be precisely measured at the same time. This principle is a cornerstone of quantum mechanics and introduces the concept of inherent uncertainty at the quantum level. In the vacuum of space, what we might think of as empty quantum fluctuations occur spontaneously with particles and antiparticles popping into and out of existence. These particles, known as virtual particles, exist for an incredibly short period of time before annihilating each other. Despite their transient nature, they have real effects and can influence the behavior of other particles. For instance, quantum fluctuations are believed to be responsible for the slight shifts in the energy levels of electrons in atoms, an effect observed and verified through experiments. Quantum fluctuations are not just a curious aspect of quantum mechanics. They are thought to have played a critical role in the formation of the universe as we know it. During the period of cosmic inflation, a brief period of rapid expansion that occurred a fraction of a second after the Big Bang, these quantum fluctuations were stretched to macroscopic scales. This process magnified the tiny fluctuations in the density of the universe, leading to the large-scale structures we observe today, such as galaxies and galaxy clusters. The patterns imprinted in the cosmic microwave background radiation are a direct result of these quantum fluctuations, offering a glimpse into the quantum origins of the universe. At the heart of quantum fluctuations is the Heisenberg uncertainty principle, which posits that certain pairs of physical properties, like position and momentum, cannot both be known exactly at the same time. This principle suggests that even what we consider a vacuum is not truly empty, but teems with virtual particles popping into and out of existence. These particles are called virtual because they cannot be directly observed. They exist temporarily, borrowing energy from the vacuum to appear for a fleeting moment before annihilating each other and returning the borrowed energy. However, under certain conditions, quantum fluctuations can lead to the creation of real particles. One such scenario occurs near the event horizon of a black hole, a phenomenon known as Hawking radiation. Stephen Hawking proposed that quantum fluctuations at the edge of a black hole, with one particle falling into the black hole and the other escaping into space, this process effectively leads to the creation of real particles from the vacuum. With the black hole losing mass over time as a result of this radiation, another context in which quantum fluctuations lead to particle creation is during the period of cosmic inflation, a theory suggesting that the universe underwent a rapid expansion shortly after the Big Bang. During inflation, quantum fluctuations were stretched to macroscopic scales, magnifying their effects. These fluctuations in the density of the early universe served as the seeds for the formation of all large-scale structures we observe today, such as galaxies and galaxy clusters. The magnification of quantum fluctuations during inflation implies that the virtual particles could freeze into real particles, contributing to the matter content of the universe. This process of particle creation from quantum fluctuations underscores the interconnectedness of quantum mechanics and cosmology, revealing the quantum underpinnings of cosmic evolution. It illustrates how the universe at its largest scales is influenced by phenomena occurring at the smallest scales, blurring the lines between the void and the tangible, between nothingness and existence. Diving deeper into the quantum realm, the role of energy in particle formation is a critical aspect that bridges the gap between the ephemeral nature of quantum fluctuations and the tangible reality of the universe. Energy plays a pivotal role in the birth of particles, acting as the catalyst that transforms the potential within quantum fluctuations into the material constituents of the cosmos. This process is rooted in one of the most famous equations in physics, E equals mc, proposed by Albert Einstein, which posits that energy, E, and mass meter are interchangeable, with c being the speed of light. This fundamental principle underscores the deep connection between energy and the creation of particles, illustrating how fluctuations in the quantum vacuum can give rise to matter in the vacuum of space. What appears to be empty is, in fact, a seething cauldron of energy due to quantum fluctuations. These fluctuations represent temporary changes in the amount of energy at a point in space, allowing for the creation of particle and particle pairs. Although these pairs typically annihilate each other almost instantaneously, returning the borrowed energy to the vacuum under certain conditions, they can become real particles. The conversion of energy into particles is a cornerstone of our understanding of the early universe and the processes that filled it with matter. For instance, in the incredibly high-energy conditions that followed the Big Bang, the universe was a hot, dense soup of energy. Some of this energy condensed into particles, following the principles laid out by Einstein's equation. The early universe went through various phases, including the electroweak epoch and the quark epoch, during which the fundamental forces of nature separated and the building blocks of matter formed and coalesced into the protons and neutrons that make up atomic nuclei today. Energy not only facilitates the creation of particles, but also influences their interactions and the structures they form. For example, the energy released during nuclear fusion processes in the hearts of stars is responsible for synthesizing the heavier elements essential for life, from carbon to iron. This transformative power of energy, from igniting stars to forging elements, highlights its fundamental role in shaping the cosmos. Navigating from the pivotal role of energy in particle formation, we find ourselves at the doorstep of another fundamental concept we talked about earlier, the Heisenberg uncertainty principle. This principle is not just a mathematical curiosity, it's a window into the inherent fuzziness of the quantum world, and has direct implications for the creation of particles from seemingly empty space. The uncertainty principle, introduced by Werner Heisenberg in 1927, states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. This inherent uncertainty is not due to experimental imperfections, but is a fundamental property of the universe at the quantum level. The uncertainty principle is intimately related to particle creation, particularly in the context of quantum fluctuations in the vacuum of space, according to quantum field theory. The vacuum isn't empty, but teems with virtual particles that continually pop into and out of existence. These particles are termed virtual because they exist temporarily. Borrowing energy from the vacuum due to the allowances made by the uncertainty principle, the principle permits these fluctuations by allowing a temporary violation of energy conservation, with the stipulation that the borrowed energy must be paid back quickly, thus preventing any violation from being directly observed. This temporary borrowing of energy makes it possible for particle-antiparticle pairs to form, returning their borrowed energy to the vacuum. Their brief existence is a direct consequence of the uncertainty inherent in their positions and momenta. In certain extreme conditions, such as near the event horizon of a black hole or during the rapid expansion of the early universe, these virtual particles can be separated and become real, observable particles. This process of particle creation from the vacuum, facilitated by the uncertainty principle, highlights the principle's crucial role in the dynamics of the quantum world and the fabric of the cosmos. In the initial fraction of a second after the Big Bang, these quantum fluctuations were stretched to macroscopic scales. This process magnified the tiny fluctuations in the density of the universe, leading to the large-scale structures we observe today, such as galaxies and galaxy clusters. The patterns imprinted in the cosmic microwave background radiation are a direct result of these quantum fluctuations. Offering a glimpse into the quantum origins of the universe, at the heart of quantum fluctuations is the Heisenberg uncertainty principle, which posits that certain pairs of physical properties, like position and momentum, cannot both be known exactly at the same time. This principle suggests that even what we consider a vacuum is not truly empty, but teems with virtual particles popping into and out of existence. These particles are called virtual because they cannot be directly observed. They exist temporarily, borrowing energy from the vacuum to appear for a fleeting moment before annihilating each other and returning the borrowed energy. However, under certain conditions, quantum fluctuations can lead to the creation of real particles. One such scenario occurs near the event horizon of a black hole, a phenomenon known as Hawking radiation. Stephen Hawking proposed that quantum fluctuations at the edge of a black hole could result in the creation of particle-antiparticle pairs. with one particle falling into the black hole and the other escaping into space. This process effectively leads to the creation of real particles from the vacuum, with the black hole losing mass over time as a result of this radiation. Another context in which quantum fluctuations lead to particle creation is during the period of cosmic inflation, a theory suggesting that the universe underwent a rapid expansion shortly after the Big Bang. During inflation, quantum fluctuations were stretched to macroscopic scales, magnifying their effects. These fluctuations in the density of the early universe served as the seeds for the formation of all large-scale structures we observe today, such as galaxies and galaxy clusters. The magnification of quantum fluctuations during inflation implies that the virtual particles could freeze into real particles, contributing to the matter content of the universe. This process of particle creation from quantum fluctuations underscores the interconnectedness of quantum mechanics and cosmology, revealing the quantum underpinnings of cosmic evolution. It illustrates how the universe at its largest scales is influenced by phenomena occurring at the smallest scales, blurring the lines between the void and the tangible, between nothingness and existence. Diving deeper into the quantum realm, the role of energy in particle formation is a critical aspect that bridges the gap between the ephemeral nature of quantum fluctuations and the tangible reality of the universe. Energy plays a pivotal role in the birth of particles, acting as the catalyst that transforms the potential within quantum fluctuations into the material constituents of the cosmos. This process is rooted in one of the most famous equations in physics, E=mc, proposed by Albert Einstein, which posits that energy, E, and mass meter are interchangeable, with c being the speed of light. This fundamental principle underscores the deep connection between energy and the creation of particles, illustrating how fluctuations in the quantum vacuum can give rise to matter. In the vacuum of space, what appears to be empty is, in fact, a seething cauldron of energy due to quantum fluctuations. These fluctuations represent temporary changes in the amount of energy at a point in space, allowing for the creation of particle-to-particle pairs, although these pairs typically annihilate each other almost instantaneously, returning the borrowed energy to the vacuum. Under certain conditions, they can become real particles. The conversion of energy into particles is a cornerstone of our understanding of the early universe and the processes that filled it with matter. For instance, in the incredibly high energy conditions that followed the Big Bang, the universe was a hot, dense soup of energy. As the universe expanded and cooled, some of this energy condensed into particles, following the principles laid out by Einstein's equation. The early universe went through various phases, including the electroweak epoch and the quark epoch, during which the fundamental forces of nature separated and the building blocks of matter formed and coalesced into the protons and neutrons that make up atomic nuclei. Today, energy not only facilitates the creation of particles, but also influences their interactions and the structures they form. For example, the energy released during nuclear fusion processes in the hearts of stars is responsible for synthesizing the heavier elements essential for life, from carbon to iron. This transformative power of energy, from igniting stars to forging elements, highlights its fundamental role in shaping the cosmos. Navigating from the pivotal role of energy in particle formation, we find ourselves at the doorstep of another fundamental concept we talked about earlier, the Heisenberg uncertainty principle. This principle is not just a mathematical curiosity. It's a window into the inherent fuzziness of the quantum world and has direct implications for the creation of particles from seemingly empty space. The uncertainty principle, introduced by Werner Heisenberg in 1927, states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. This inherent uncertainty is not due to experimental imperfections, but is a fundamental property of the universe at the quantum level. The uncertainty principle is intimately related to particle creation, particularly in the context of quantum fluctuations in the vacuum of space. According to quantum field theory, the vacuum isn't empty, but teems with virtual particles that continually pop into and out of existence. These particles are termed virtual because they exist temporarily, borrowing energy from the vacuum due to the allowances made by the uncertainty principle. The principle permits these fluctuations by allowing a temporary violation of energy conservation, with the stipulation that the borrowed energy must be paid back quickly, thus preventing any violation from being directly observed. This temporary borrowing of energy makes it possible for particle-antiparticle pairs to form spontaneously, although these pairs usually annihilate each other almost immediately. Returning their borrowed energy to the vacuum is a direct consequence of the uncertainty inherent in their positions and momenta. In certain extreme conditions, such as near the event horizon of a black hole or during the rapid expansion of the early universe, these virtual particles can be separated and become real, observable particles. This process of particle creation from the vacuum, facilitated by the uncertainty principle, highlights the principle's crucial role in the dynamics of the quantum world and the fabric of the cosmos. In the initial fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It was filled with a quark-gluon plasma, a state of matter in which quarks' fundamental particles that later formed protons and neutrons were not confined within atomic nuclei, but were free in a soup of gluons, particles that mediate the strong force holding quarks together. As the universe expanded and cooled, it reached a temperature where quarks could coalesce to form protons and neutrons, the building blocks of atomic nuclei. This epoch, known as the Hadron Epoch, occurred within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons marked a pivotal moment in the early universe, setting the stage for the creation of more complex forms of matter. Following the Hadron Epoch, the universe continued to cool, leading to the Lepton Epoch, which lasted from about 1 second to a few minutes post-Big Bang. During this period, leptons, such as electrons, were the dominant form of matter. The universe was still too hot for protons and neutrons to combine into nuclei with these electrons. The most critical event related to particle formation came next: nucleosynthesis, a process that occurred within the first few minutes after the Big Bang. During this period, the universe had cooled sufficiently for protons and neutrons to begin combining to form the nuclei of the simplest elements: hydrogen, helium, and trace amounts of lithium and beryllium. This primordial nucleosynthesis was responsible for creating most of the helium in the universe, alongside the hydrogen that did not bind into helium nuclei. It's important to note that these were not yet complete atoms in the way we think of them today, with electrons orbiting a nucleus. The universe remained too hot for electrons to be captured into orbits around nuclei, forming neutral atoms. This formation of neutral atoms, a process known as recombination, would not occur until approximately 380,000 years after the Big Bang, leading to the decoupling of matter and radiation and the release of the cosmic microwave background radiation, the afterglow of the Big Bang, which provides us with a snapshot of the universe at that time. Now, let's venture further into the fascinating epoch when the fundamental forces of nature began to delineate and define the evolving cosmos. This narrative of separation is a cornerstone in understanding the universe's intricate tapestry. From its most nascent moments to the richly structured expanse we observe today. Initially, in the universe's first moments, all forces were unified in a singular force, a testament to the extreme conditions of temperature and density that pervaded the cosmos. The Big Bang, these quantum fluctuations were stretched to macroscopic scales. This process magnified the tiny fluctuations in the density of the universe, leading to the large-scale structures we observe today, such as galaxies and galaxy clusters. The patterns imprinted in the cosmic microwave background radiation are a direct result of these quantum fluctuations. Offering a glimpse into the quantum origins of the universe, at the heart of quantum fluctuations is the Heisenberg uncertainty principle, which posits that certain pairs of physical properties, like position and momentum, cannot both be known exactly at the same time. This principle suggests that even what we consider a vacuum is not truly empty, but teems with virtual particles popping into and out of existence. These particles are called virtual because they cannot be directly observed. They exist temporarily, borrowing energy from the vacuum to appear for a fleeting moment before annihilating each other and returning the borrowed energy. However, under certain conditions, quantum fluctuations can lead to the creation of real particles. One such scenario occurs near the event horizon of a black hole, a phenomenon known as Hawking radiation. Stephen Hawking proposed that quantum fluctuations at the edge of a black hole could result in the creation of particle-antiparticle pairs, with one particle falling into the black hole and the other escaping into space. This process effectively leads to the creation of real particles from the vacuum, with the black hole losing mass over time as a result of this radiation. Another context in which quantum fluctuations lead to particle creation is during the period of cosmic inflation, a theory suggesting that the universe underwent a rapid expansion shortly after the Big Bang. During inflation, quantum fluctuations were stretched to macroscopic scales, magnifying their effects. These fluctuations in the density of the early universe served as the seeds for the formation of all large-scale structures we observe today, such as galaxies and galaxy clusters. The magnification of quantum fluctuations during inflation implies that the virtual particles could freeze into real particles, contributing to the matter content of the universe. This process of particle creation from quantum fluctuations underscores the interconnectedness of quantum mechanics and cosmology, revealing the quantum underpinnings of cosmic evolution. It illustrates how the universe at its largest scales is influenced by phenomena occurring at the smallest scales, blurring the lines between the void and the tangible, between nothingness and existence. Diving deeper into the quantum realm, the role of energy in particle formation is a critical aspect that bridges the gap between the ephemeral nature of quantum fluctuations and the tangible reality of the universe. Energy plays a pivotal role in the birth of particles, acting as the catalyst that transforms the potential within quantum fluctuations into the material constituents of the cosmos. This process is rooted in one of the most famous equations in physics, E=mc, proposed by Albert Einstein, which posits that energy, E, and mass meter are interchangeable, with c being the speed of light. This fundamental principle underscores the deep connection between energy and the creation of particles, illustrating how fluctuations in the quantum vacuum can give rise to matter. In the vacuum of space, what appears to be empty is, in fact, a seething cauldron of energy due to quantum fluctuations. These fluctuations represent temporary changes in the amount of energy at a point in space, allowing for the creation of particle-antiparticle pairs, although these pairs typically annihilate each other almost instantaneously, returning the borrowed energy to the vacuum. Under certain conditions, they can become real particles. The conversion of energy into particles is a cornerstone of our understanding of the early universe and the processes that filled it with matter. For instance, in the incredibly high energy conditions that followed the Big Bang, the universe was a hot, dense soup of energy. As the universe expanded and cooled, some of this energy condensed into particles, following the principles laid out by Einstein's equation. The early universe went through various phases, including the electroweak epoch and the quark epoch, during which the fundamental forces of nature separated and the building blocks of matter formed and coalesced into the protons and neutrons that make up atomic nuclei today. Energy not only facilitates the creation of particles, but also influences their interactions and the structures they form. For example, the energy released during nuclear fusion processes in the hearts of stars is responsible for synthesizing the heavier elements essential for life, from carbon to iron. This transformative power of energy, from igniting stars to forging elements, highlights its fundamental role in shaping the cosmos. Navigating from the pivotal role of energy in particle formation, we find ourselves at the doorstep of another fundamental concept we talked about earlier, the Heisenberg uncertainty principle. This principle is not just a mathematical curiosity. It's a window into the inherent fuzziness of the quantum world and has direct implications for the creation of particles from seemingly empty space. The uncertainty principle, introduced by Werner Heisenberg in 1927, states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. This inherent uncertainty is not due to experimental imperfections, but is a fundamental property of the universe at the quantum level. The uncertainty principle is intimately related to particle creation, particularly in the context of quantum fluctuations in the vacuum of space. According to quantum field theory, the vacuum isn't empty, but teems with virtual particles that continually pop into and out of existence. These particles are termed virtual because they exist temporarily, borrowing energy from the vacuum due to the allowances made by the uncertainty principle. The principle permits these fluctuations by allowing a temporary violation of energy conservation, with the stipulation that the borrowed energy must be paid back quickly, thus preventing any violation from being directly observed. This temporary borrowing of energy makes it possible for particle-antiparticle pairs to form spontaneously, although these pairs usually annihilate each other almost immediately. Returning their borrowed energy to the vacuum is a direct consequence of the uncertainty inherent in their positions and momenta. In certain extreme conditions, such as near the event horizon of a black hole or during the rapid expansion of the early universe, these virtual particles can be separated and become real, observable particles. This process of particle creation from the vacuum, facilitated by the uncertainty principle, highlights the principle's crucial role in the dynamics of the quantum world and the fabric of the cosmos. In the initial fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It was filled with a quark-gluon plasma, a state of matter in which quarks' fundamental particles that later formed protons and neutrons were not confined within atomic nuclei, but were free in a soup of gluons, particles that mediate the strong force holding quarks together. As the universe expanded and cooled, it reached a temperature where quarks could coalesce to form protons and neutrons, the building blocks of atomic nuclei. This epoch, known as the Hadron Epoch, occurred within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons marked a pivotal moment in the early universe, setting the stage for the creation of more complex forms of matter. Following the Hadron Epoch, the universe continued to cool, leading to the Lepton Epoch, which lasted from about 1 second to a few minutes post-Big Bang. During this period, leptons, such as electrons, were the dominant form of matter. The universe was still too hot for protons and neutrons to combine into nuclei with these electrons. The most critical event related to particle formation came next: nucleosynthesis, a process that occurred within the first few minutes after the Big Bang. During this period, the universe had cooled sufficiently for protons and neutrons to begin combining to form the nuclei of the simplest elements: hydrogen, helium, and trace amounts of lithium and beryllium. This primordial nucleosynthesis was responsible for creating most of the helium in the universe, alongside the hydrogen that did not bind into helium nuclei. It's important to note that these were not yet complete atoms in the way we think of them today, with electrons orbiting a nucleus. The universe remained too hot for electrons to be captured into orbits around nuclei, forming neutral atoms. This formation of neutral atoms, a process known as recombination, would not occur until approximately 380,000 years after the Big Bang, leading to the decoupling of matter and radiation and the release of the cosmic microwave background radiation, the afterglow of the Big Bang, which provides us with a snapshot of the universe at that time. Now, let's venture further into the fascinating epoch when the fundamental forces of nature began to delineate and define the evolving cosmos. This narrative of separation is a cornerstone in understanding the universe's intricate tapestry. From its most nascent moments to the richly structured expanse we observe today. Initially, in the universe's first moments, all forces were unified in a singular force, a testament to the extreme conditions of temperature and density that pervaded the cosmos. Way for the universe's transition from a hot, dense state to a cooler, structured one, capable of supporting complex structures such as stars and galaxies. It signified the end of the universe's dark ages, a time before the first stars ignited, and set the stage for the gravitational collapse of matter into the first stars and galaxies. These stars would further enrich the cosmos with heavier elements through stellar nucleosynthesis, seeding the universe with the ingredients necessary for planets and life. Nucleosynthesis, the process by which the natural abundances of the chemical elements within stars were formed, played a crucial role in creating the diversity of elements that we observe in the universe today. Following the formation of the first atoms, the universe was primarily composed of hydrogen and helium, the simplest and most abundant elements. However, the complex and varied world around us, from the air we breathe to the materials that make up the earth, and even the components of our own bodies, requires a much broader array of elements. Nucleosynthesis provided the processes necessary. To forge these elements, acting as the cosmic furnace that transformed the primordial simplicity of the early universe into a rich tapestry of chemical diversity. The process of nucleosynthesis occurred in several stages and environments, starting with the Big Bang itself. Big Bang nucleosynthesis, occurring within the first minutes of the universe, produced the lightest elements, including hydrogen, helium, and trace amounts of lithium and beryllium. However, this process could not account for the creation of heavier elements that are essential for life and the structure of the cosmos. The next phase of nucleosynthesis took place within stars. Stars are the universe's factories for element production, transforming lighter elements into heavier ones through nuclear fusion in their core. In the life cycle of a star, hydrogen nuclei fuse to form helium in a process known as hydrogen burning. As stars age and their cores heat up, they can fuse helium into carbon, and in more massive stars, the process continues, forming elements up to iron through successive stages of nuclear burning, such as carbon burning, neon burning, oxygen burning, and silicon burning. However, the creation of elements heavier than iron requires a different set of processes. As these elements cannot be formed through fusion in stellar cores under normal circumstances due to their energy requirements, instead, processes such as the R process, rapid neutron capture, and the S process, slow neutron capture, come into play. Primarily during supernova explosions and in the outer shells of asymptotic giant branch AGB stars, supernova, the cataclysmic explosions that mark the death of massive stars, provide the necessary conditions for the R process, where a dense flux of neutrons is absorbed by atomic nuclei, leading to the creation of many of the heavier elements in the periodic table. The S process occurs in the more serene environs of AGB stars, where neutrons are captured more slowly, allowing for the creation of elements like barium and lead. The diverse elements forged by nucleosynthesis are eventually spread throughout the galaxy by stellar winds and supernova explosions, seeding interstellar clouds with the materials needed for the next generation of stars, planets, and eventually, life. This cycle of star birth, nucleosynthesis, and death, followed by the reformation of new stellar systems, has enriched the universe with a complex chemistry over billions of years. Particle accelerators and experimental physics. Particle accelerators are sophisticated machines that propel charged particles, such as protons or electrons, to high speeds and smash them together or against targets, generating conditions that mimic those just after the Big Bang. These groundbreaking tools allow scientists to investigate the fundamental properties of matter and the forces that govern the interactions between particles by accelerating particles to nearly the speed of light and then colliding them. Particle accelerators enable researchers to break down atomic components into their constituent parts, revealing particles and phenomena not observable under normal conditions. The workings of a particle accelerator involve using electric fields to accelerate particles and magnetic fields to steer and focus them along a specified path, which can be circular, as in synchrotrons and storage rings, or linear, as in linear accelerators, linacs. When these high-energy particles collide, they produce a variety of new particles, allowing scientists to study the rules of particle physics in environments of extreme energy densities, similar to those that existed just after the Big Bang. There are several types of particle accelerators, each serving different purposes in the field of research and beyond. For instance, the Large Hadron Collider, LHC, at CERN, near Geneva, Switzerland, is the world's largest and most powerful particle accelerator, designed to probe deeper into the mysteries of the universe, such as the properties of the Higgs boson, dark matter, and other fundamental questions about the nature of reality beyond their fundamental scientific applications. Particle accelerators have practical uses in various fields, including medicine, where they are used for cancer treatment through radiation therapy, and in producing isotopes for medical diagnostics. In industry, for materials processing and the creation of semiconductors, and in art and archaeology, for analyzing paintings and artifacts without damaging them. The development and operation of particle accelerators are feats of engineering and physics, combining advanced technologies in superconducting magnets, vacuum systems, and particle detection to explore the frontiers of human knowledge. These machines are not just tools for discovery, but are also catalysts for technological innovation, driving advances in numerous fields and contributing to the technological infrastructure of society. Particle accelerators have been instrumental in advancing our understanding of the fundamental aspects of the universe, leading to numerous significant discoveries that have shaped modern physics. These machines, by propelling particles to high velocities and facilitating their collisions, have allowed scientists to probe the deepest secrets of the universe, revealing the existence of particles and forces that constitute the fabric of everything around us. One of the most groundbreaking discoveries made with the aid of particle accelerators was the identification of the Higgs boson. In 2012, scientists at CERN's Large Hadron Collider LHC announced they had detected a particle consistent with the Higgs boson, often referred to as the God particle. This particle, predicted by the Standard Model of particle physics, is fundamental to understanding why other particles have mass. The discovery of the Higgs boson was a monumental moment in the field of particle physics, confirming a key pillar of the Standard Model and contributing to the Nobel Prize in Physics for Francois Englert and Peter Higgs in 2013. Particle accelerators have also been pivotal in confirming the existence of quarks, the building blocks of protons and neutrons. In the late 1960s and early 1970s, supporting the quark model proposed by physicists Murray Gell-Mann and George Tisvik in the 1960 South. This was a significant step forward in our understanding of the structure of matter, establishing quarks as fundamental constituents of matter. Furthermore, accelerators have facilitated the study of antimatter, particles that are identical to matter particles but with opposite charge. Experiments at CERN and other facilities have allowed physicists to create, trap, and study antimatter particles, such as antihydrogen. These studies are crucial for testing the fundamental symmetries of the universe, and for understanding why the universe is composed mainly of matter, despite the Big Bang theory predicting equal amounts of matter and antimatter. Particle accelerators have also enabled the discovery of a plethora of subatomic particles, including W and Z bosons, which mediate the weak nuclear force responsible for radioactive decay. The discovery of these particles in the 1980s at CERN provided critical proof of the electroweak theory, which unifies the electromagnetic and weak forces. One of the key achievements in efforts to develop a unified theory of fundamental forces. Beyond fundamental discoveries, particle accelerators have contributed to advancements in medical treatments, such as cancer therapy through particle beams, and in the development of technologies like the World Wide Web, initially created at CERN to facilitate information sharing among scientists now. How do these experiments in particle physics validate theoretical predictions? The interplay between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain the properties and behaviors of particles and the forces that govern their interactions. These models often make precise predictions about the outcomes of certain interactions or the existence of previously unobserved particles. To test these predictions, experimental physicists design and conduct experiments using particle accelerators. These machines accelerate particles to high energies and then collide them, creating conditions that allow for the observation of phenomena that are not accessible under normal circumstances. The detectors surrounding the collision, points capture and record the particles produced in these collisions, and sophisticated data analysis techniques are employed to interpret the results. A significant aspect of validating theoretical predictions, the interplay between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain the properties and behaviors of particles and the forces that govern their interactions. These models often make precise predictions about the outcomes of certain interactions or the existence of previously unobserved particles. To test these predictions, experimental physicists design and conduct experiments using particle accelerators. These machines accelerate particles to high energies and then collide them, points capture, and record the particles produced in these collisions, and sophisticated data analysis techniques are employed to interpret the results. A significant aspect of validating theoretical predictions is the ability to reproduce experimental results. In particle physics, this often means that multiple experiments, sometimes at different facilities around the world, must observe the same phenomena under similar conditions. This replication of results adds artifacts of the experimental setup. The standard model of particle physics. The standard model of particle physics is a theory that describes three of the four known fundamental forces in the universe, the electromagnetic, weak, and strong nuclear forces, and classifies all known elementary particles. It is a cornerstone of modern physics and represents the best understanding scientists have of how the fundamental constituents of the universe behave and interact. The model has been developed over several decades, starting in the mid-20th century. Through the collaborative efforts of physicists around the world, at its core, the standard model is built on the foundation of quantum mechanics and special relativity, incorporating both into a unified framework known as quantum field theory. The model categorizes elementary particles into two main groups, fermions and bosons. Fermions are the building blocks of matter, divided into quarks and leptons, including particles like electrons and the quarks that make up protons and neutrons. Bosons are force carrier, particles that mediate the fundamental forces. For instance, photons carry the electromagnetic force, while gluons are responsible for the strong force. A significant triumph of the standard model was the prediction and subsequent discovery of the Higgs boson, a particle that provides mass to other particles through the Higgs mechanism. This discovery at the Large Hadron Collider in 2012 filled a crucial gap in the model and was hailed as one of the most significant achievements in physics, confirming the existence of the Higgs field and its associated particle. Despite its successes, the standard model is not complete. It does not incorporate the fourth fundamental force, gravity, described by general relativity, nor does it account for the dark matter and dark energy that appear to constitute most of the universe's mass energy content. Additionally, the model's inability to incorporate the gravitational force or predict the masses of elementary particles suggests that it is a part of a more comprehensive theory yet to be discovered. While the standard model of particle physics stands as a remarkably successful theoretical framework, it also has its limitations, marking areas where our current understanding of the universe is incomplete. These limitations not only highlight the boundaries of the model's applicability, but also point toward new physics beyond what we currently know, guiding researchers in their quest to uncover a more comprehensive theory of the fundamental forces and particles. One of the most significant limitations of the standard model is its inability to incorporate gravity. Gravity, described by Einstein's theory of general relativity, is a fundamental force that governs the structure and dynamics of the cosmos on the largest scales, from the orbits of planets to the evolution of galaxies and the universe itself. However, the standard model is based on the framework of quantum field theory, which does not naturally include gravity. This discrepancy between the theories of the very large general relativity and the very small quantum mechanics remains one of the most profound challenges in physics. Another limitation is the standard model's silence on the nature of dark matter and dark energy. Observations of the universe suggest that about 85% of its matter content is dark matter, which does not emit, absorb, or reflect light, and is detectable only through its gravitational effects. Dark energy contributing to about 68% of the total energy content of the universe, is thought to be responsible for its accelerating expansion. The standard model, however, does not predict the existence of dark matter particles, nor does it account for the properties of dark energy, leaving a significant portion of the universe unexplained. The standard model also cannot explain the matter-antimatter asymmetry observed in the universe. According to the model, the Big Bang should have produced equal amounts of matter and antimatter, which would annihilate each other, leaving behind a universe filled with radiation. However, the observable universe is dominated by matter, suggesting that processes not accounted for in the standard model must have given matter an edge over antimatter. The standard model does not provide a satisfactory explanation for the masses of neutrinos. Initially, the model assumed that neutrinos were massless, but experiments have shown that they have a small mass. This discovery has necessitated revisions to the model, but has also opened up new questions about the origins of neutrino mass and their role in the universe. The standard model is a patchwork of particles and forces without a unifying principle that could explain why this particular set of particles and forces exists. The search for a theory of everything that would unify all fundamental forces, including gravity, and offer a more fundamental understanding of the particles themselves, remains a major goal of theoretical physics beyond the Standard Model. Matter and dark energy are two of the most profound mysteries in modern cosmology, representing components of the universe that are invisible and undetectable by traditional means, but whose presence is inferred from their gravitational effects and the impact on the universe's expansion. Together, they compose about 95% of the total mass energy content of the universe, with dark matter accounting for approximately 27% and dark energy for about 68%, leaving ordinary matter, everything we can see and interact with, making up just a small fraction. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it completely invisible to electromagnetic radiation and thus extremely difficult to detect directly. Its existence was first posited in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies within clusters were moving at speeds that implied the presence of much more mass than could be accounted for by the visible matter alone. Since then, further evidence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation has supported the existence of dark matter. Despite being invisible, dark matter exerts gravitational forces, influencing the structure and formation of galaxies and galaxy clusters. It acts as a cosmic scaffold around which visible matter congregates and forms into the large-scale structures observed in the universe. Dark energy, on the other hand, is a mysterious force that is driving the accelerated expansion of the universe. The discovery of dark energy in the late 1990s was a significant surprise to astronomers who had expected that the universe's expansion might be slowing down due to the gravitational attraction of its contents. Instead, observations of distant supernova revealed that galaxies are moving away from each other at an accelerating rate. Dark energy is thought to be a property of space itself, evenly distributed throughout the universe, and not diluting as space expands. Its nature is even less understood than that of dark matter, and it poses a fundamental challenge to our understanding of the laws of physics, as it does not fit neatly into the Standard Model of particle physics or the theory of general relativity. Dark matter, which constitutes about 27% of the universe, interacts with ordinary matter through gravity. It does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Dark matter's presence is inferred from its gravitational pull on galaxies and galaxy clusters, influencing their rotation rates and distribution. This invisible matter acts as a cosmic scaffold, providing the gravitational framework necessary for galaxies to form and cluster together. During the early universe, dark matter's gravitational pull helped to amplify the slight irregularities left by quantum fluctuations, leading to the formation of large-scale structures like galaxies and clusters of galaxies. These structures created the potential wells within which ordinary matter could gather and cool, leading to star formation and the subsequent synthesis of heavier elements through nucleosynthesis in stars. Dark energy, on the other hand, accounts for approximately 68% of the universe and is thought to be responsible for its accelerated expansion. Unlike dark matter, dark energy does not cluster but is uniformly distributed across space, exerting a repulsive force that counteracts gravity. The exact nature of dark energy remains one of the biggest mysteries in physics, but its effect on the universe's expansion rate has critical implications for particle formation and the evolution of the cosmos. The accelerated expansion affects the density and temperature of the universe over time, influencing the rate at which structures form and evolve. This expansion impacts the cooling of the universe and the regions where particles can come together to form atoms, molecules, and eventually the stars and galaxies. Supersymmetry and fermions, which make up matter according to supersymmetry. For every boson in the Standard Model, there exists a corresponding fermion partner, and vice versa, that has not yet been observed. These partner particles are known as superpartners, with names that mirror their Standard Model counterparts, and selectrons for superpartners of electrons. The allure of supersymmetry lies in its potential to address several unresolved issues within the Standard Model of particle physics and cosmology. One of the most significant challenges it aims to solve is the hierarchy problem, which concerns the vast difference in strength between the gravitational force and the other. Fundamental forces supersymmetry suggests that new symmetries in the laws of physics can stabilize the mass of the Higgs boson against quantum corrections that could otherwise make it much heavier, thus providing a natural explanation for the weak scale and the stability of the Higgs boson's mass. Moreover, supersymmetry is a leading candidate for explaining dark matter, a mysterious substance that makes up about 27% of the universe, but does not emit, absorb, or reflect light. Supersymmetric particles, particularly the lightest supersymmetric particle, LSP, are stable, electrically neutral, and only weakly interacting. The gravitational effects, attributed to dark matter in galaxies and clusters of galaxies, despite its elegant theoretical foundation and the compelling solutions it offers to some of physics' most perplexing questions, direct evidence for supersymmetry has yet to be found. Particle accelerators, such as the Large Hadron Collider, LHC, at CERN, have conducted extensive searches for superpartners of known particles. However, as of my last update, these efforts have not yet resulted in the discovery of supersymmetric particles, leading to increased constraints on supersymmetric models and pushing the predicted masses of superpartners to higher values outside the reach of current experiments. Now, are there theories that propose particles beyond the standard model? There are several compelling theories that propose the existence of particles beyond those described in the standard model of particle physics. These theories aim to address the limitations and unanswered questions left by the standard model, such as the nature of dark matter, the hierarchy problem, and the unification of forces. Among the most prominent of these theories are supersymmetry, SUSY, string theory, and theories involving extra dimensions. Supersymmetry, as mentioned earlier, extends the standard model by introducing a superpartner for each particle, effectively doubling the particle zoo. These superpartners, which have not yet been observed, could help explain the dark matter mystery and offer a solution to the hierarchy problem by stabilizing the mass of the Higgs boson. Supersymmetry predicts a range of new particles, such as the gluon, the superpartner of the gluon, and the gravitino, the superpartner of the graviton, a hypothetical particle associated with gravity. String theory, another leading candidate for extending our understanding of the fundamental constituents of the universe, proposes that the elementary particles are not point-like dots, but rather tiny, vibrating strings. The vibrational modes of these strings correspond to different particles, with their vibration patterns determining the particle's properties. String theory inherently includes supersymmetry and predicts the existence of many new particles, including those responsible for gravity, potentially offering a way to unify all fundamental forces. It also suggests the existence of additional spatial dimensions beyond the familiar three. Theories involving extra dimensions, such as those proposed in various string theory formulations and in approaches like the Bragg-Urald scenario, suggest that our universe might have more than the three spatial dimensions we experience. These extra dimensions could be quantified and hidden on scales too small for current experiments to detect directly. Particles could propagate through these extra dimensions, potentially explaining why gravity is so much weaker than the other fundamental forces and suggesting the existence of particles associated with these. By introducing additional symmetry groups, these theories predict the existence of new particles, such as heavy-gauge bosons, which could mediate transitions between quarks and leptons, changing one type of particle into another. Model's shortcomings. Direct experimental evidence for particles beyond the standard model remains elusive. Particle accelerators, such as the Large Hadron Collider, are at the forefront of searching for these hypothetical particles. Discovering them would not only validate these theories, but also dramatically change our understanding of the universe's fundamental structure and forces. The role of gravity in particle formation. Gravity scales to the vastness of galactic structures. While its effects are subtle in the realm of particle physics, gravity's role becomes increasingly significant. On particle formation can be seen in the process of star formation. The intense pressure and temperature in the cores of these nascent stars initiate the fusion of hydrogen atoms into helium, releasing energy in the process. This fusion, the heart of stellar nucleosynthesis, generates the heavier elements essential For life and the diversity of the chemical elements found throughout the universe, gravity is instrumental in the formation of black holes, regions of space-time where gravitational forces are so strong that nothing, not even light, can escape. In the extreme conditions near a black hole's event horizon, theoretical processes, such as Hawking radiation, predict the creation of particle and particle pairs from the vacuum of space itself. While one particle falls into the black hole, the other escapes, suggesting a fascinating interplay between gravity and quantum mechanics that could influence particle formation on a cosmological scale. Gravity's role in particle formation extends to the very structure of the universe. The distribution of matter, from the filamentary structures that make up the cosmic web to the formation of galaxies and galaxy clusters, is governed by gravitational attraction. This distribution, in turn, determines the regions where particles can come together to form stars, electromagnetic and nuclear forces at small scales. Its cumulative effect over cosmic timescales and distances is crucial for understanding the universe's evolution, the formation of particles, stars, and galaxies, and the very structure of the cosmos, are all testament to gravity's foundational role in shaping the universe from its earliest moments to the present day. The theory of inflation. The theory of inflation is a pivotal concept in cosmology that addresses some of the most fundamental questions about the early universe. Proposed in the early 1980s by physicists, including Alan Guth and Andre Linde, inflation posits that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion, much faster than the speed of light, stretched the size of the universe by many orders of magnitude in a blink of an eye. Inflation was introduced to solve several problems inherent in the Big Bang theory as it stood at the time. One of these was the horizon problem, which questions how parts of the universe that are now widely separated could have come to be at the same. Explains this by proposing that these regions were once close together before being driven apart by the swift expansion, allowing them to come into thermal equilibrium before being separated beyond the horizon of causal connection. Another issue addressed by inflation is the flatness problem. Observations suggest that the universe is remarkably flat, meaning it conforms to the geometry described by Euclidean geometry over large scales, requiring a fine-tuning of initial conditions if the universe expanded at a steady rate from the Big Bang. Inflation elegantly solves this by diluting any curvature in the early universe's fabric, leading to a universe that appears flat on large scales. As observed, inflation also provides an explanation for the origin of the large-scale structure of the universe. The theory predicts that tiny quantum fluctuations in the early universe were. These fluctuations then served as the seeds for the growth of structure in the universe, such as galaxies and galaxy clusters, through gravitational attraction. The theory of inflation is supported by observations of the cosmic microwave background radiation, the afterglow of the Big Bang, which shows patterns of slight temperature variations consistent with the predictions of inflation. These observations have solidified inflation's role as a cornerstone of our understanding of the early universe. Despite it being a theory that pushes the boundaries of current physics, while the theory of inflation has greatly enhanced our understanding of the cosmos's early moments, it also raises new questions, such as what caused inflation to start and what stopped it. Various models of inflation have been proposed, some incorporating ideas from quantum field theory and string theory, aiming to provide a more complete picture of these dynamics. How does inflation explain the uniformity of the cosmic microwave? Background. Inflation theory offers a compelling explanation for the uniformity observed in the cosmic microwave background, CMB, the faint afterglow of radiation permeating the universe from the Big Bang. The CMB presents a nearly uniform temperature across the sky, with incredibly slight variations about 1 part in 100,000. This uniformity, coupled with the isotropy sameness in all directions of the universe on large scales, posed a significant puzzle for cosmologists before the advent of inflation theory. Given the vastness of the universe and the finite speed of light, regions on opposite sides of the observable universe haven't had enough time since the Big Bang to exchange heat or light and come to a thermal equilibrium. This dilemma, known as the horizon problem, raised questions about how the CMB could be so remarkably uniform. Inflation addresses this conundrum by proposing a period of exponential expansion shortly after the Big Bang. According to inflationary theory, the observable universe expanded from a tiny subatomic size to a macroscopic size in less than a trillionth of a second. This rapid expansion means that regions now on opposite sides of the observable universe were once close together, well within causal contact. Before inflation drove them apart, these regions were able to come to a thermal equilibrium, energy and smoothing out any temperature differences before being stretched across the sky by inflation. Thus, when we look at the CMB, we are seeing a snapshot of a much smaller uniform universe stretched across the vastness of space, explaining its uniform temperature. The slight variations in temperature that we do observe in the CMB, then, are attributed to quantum fluctuations in the density of the universe that were present just before inflation occurred. These fluctuations, once minuscule, were amplified by the inflationary expansion to stretch across cosmic scales, forming the seeds for the large-scale structure of the universe, such as galaxies and clusters of galaxies. The patterns of these fluctuations in the CMB have been precisely measured by experiments such as the Cosmic Background Explorer (COBE), the Wilkinson Microwave Anisotropy Probe (WMAP), and the Planck satellite. And symmetry antimatter is a fundamental concept in physics, mirroring the properties of matter but with opposite charges. For every type of particle that constitutes matter, there exists a corresponding antiparticle that makes up antimatter. These antiparticles possess the same mass as their matter counterparts, but have opposite electric charge and other quantum numbers. The most familiar examples include the positron, the antiparticle of the electron, which carries a positive charge, and the antiproton, which has the same mass as a proton but a negative charge. The existence of antimatter was first predicted by the British physicist Paul Dirac in 1928, based on his work extending the equations of quantum mechanics to incorporate the theory of special relativity. Dirac's equations suggested the presence of particles that had the same mass as electrons but opposite charge, a prediction that was confirmed in 1932 with the discovery of the positron by Carl Anderson. This discovery was groundbreaking, as it provided the first evidence of antimatter and validated Dirac's theoretical framework. When a particle of matter encounters its corresponding antiparticle, the two annihilate each other in a burst of energy, typically producing gamma rays. This process of annihilation demonstrates the equivalence of mass and energy, as described by Einstein's E=mc equation, and is a fundamental aspect of antimatter's interaction with matter. Antimatter is not just a theoretical curiosity. It has practical applications and implications. In medicine, for example, positron emission tomography (PET) scans rely on the detection of gamma rays from positron annihilation to create detailed images of the body. Furthermore, understanding antimatter is crucial for advancing our knowledge of the universe. Cosmologists study antimatter to address fundamental questions about the Big Bang and why the observable universe appears to be composed almost entirely of matter, despite theories predicting equal amounts of matter and antimatter were produced in the universe's early moments. The investigation of antimatter also pushes the boundaries of particle physics, challenging scientists to create, trap, and study antiparticles in laboratory conditions. Experiments with anti-hydrogen atoms, for instance, aim to compare the properties of hydrogen and antihydrogen to test the fundamental symmetries of nature. These studies could reveal new physics beyond the standard model, offering insights into the forces and particles that shape our universe. Now, let's talk a bit about CP violation and how it relates to matter-antimatter asymmetry. CP violation refers to a fundamental phenomenon in particle physics where the combined operation of charge conjugation C and parity inversion P is not conserved. In simpler terms, it means that certain processes involving the transformation of particles into their corresponding antiparticles do not occur in the same way. When the charges and spatial orientations are reversed, CP violation is significant in the context of understanding the matter-antimatter asymmetry in the universe. In the early universe, matter and antimatter were produced in nearly equal amounts during particle-and-particle creation processes. However, if all physical processes respected CP symmetry perfectly, matter and antimatter would have annihilated each other completely, leaving behind a universe devoid of matter. The observed matter-antimatter asymmetry suggests that there must be processes where CP symmetry is violated, favoring the production of matter over antimatter. This violation of CP symmetry allows for subtle differences in the behavior of particles and antiparticles, leading to a slight excess of matter that ultimately gave rise to the structures we see in the universe today. Observed in certain rare decays of elementary particles, such as neutral kaons and B mesons, these experiments have provided crucial insights into the mechanisms responsible for generating the matter-antimatter asymmetry in the early universe. However, the exact origin of CP violation and its connection to the observed matter-antimatter asymmetry remain active areas of research in particle physics. Philosophical and conceptual questions: can we truly understand the origin of the universe? This question has captivated scientists, philosophers, and theologians alike for centuries. As we delve into the depths of cosmology and particle physics, we uncover glimpses of the cosmic drama that unfolded billions of years ago. Yet, despite our best efforts, there remains a veil of mystery shrouding the ultimate genesis of the cosmos. Theories such as the Big Bang provide a framework for understanding the evolution of the universe from its earliest moments. But when we peer back to the very instant of creation, we encounter a realm where the laws of physics break down, and our conventional understanding falters. It is a realm of extreme temperatures, densities, and energies, where the fabric of space-time itself undergoes profound transformations. In our quest to comprehend the origin of the universe, we confront the limits of human cognition and the boundaries of scientific inquiry. Can we ever hope to unravel the mysteries of existence with our finite minds and empirical methods? Or are there realms of knowledge that lie beyond the reach of human understanding? Some argue that the pursuit of understanding is an inherent aspect of the human condition, driving us to explore, question, and seek answers to the deepest mysteries of existence. Others contend that there are limits to what we can know, and that some aspects of reality may forever elude our grasp. How does the concept of nothing fit into modern physics? It's a question that challenges our fundamental understanding of reality. In the realm of modern physics, nothing isn't simply an absence of matter or energy. Instead, it's a complex and dynamic landscape governed by the laws of quantum mechanics. In quantum physics, the vacuum of space is far from empty. It's teeming with virtual particles, spontaneously popping in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This phenomenon, known as vacuum fluctuations, suggests that even in the absence of particles, the fabric of space-time is seething with activity. Moreover, the concept of nothing is intertwined with the mysteries of the universe's origin. Big Bang theory posits that the universe emerged from a singularity, a point of infinite density and temperature. But what preceded the Big Bang? Was there truly nothing before the universe began its expansion? Or are there realms of existence beyond our current understanding? Research in particle physics has far-reaching implications that extend beyond the confines of the laboratory, offering numerous benefits to society. While the subject matter might seem esoteric, the advancements made in particle physics have yielded tangible outcomes that impact our daily lives. One significant contribution of particle physics research is its role in medical imaging and treatment. Technologies such as PET positron emission tomography and MRI magnetic resonance imaging have their roots in particle physics research. These imaging techniques are crucial for diagnosing medical conditions and guiding treatment plans, improving healthcare outcomes for millions of people worldwide. Additionally, particle physics has paved the way for advancements in radiation therapy for cancer treatment. Techniques such as proton therapy, which utilizes beams of protons to precisely target tumors while minimizing damage to surrounding healthy tissues, have emerged from particle physics research. These therapies offer more effective and less invasive treatment options for cancer patients. Research in particle physics has contributed to the development of innovative materials and technologies. For example, the World Wide Web, invented at CERN to facilitate communication among researchers, has transformed the way information is accessed and shared globally. Furthermore, advancements in particle detector technologies have led to the creation of more sensitive detectors used in security screening, environmental monitoring, and even archaeological exploration. The pursuit of fundamental knowledge in particle physics often drives advancements in other scientific disciplines. Collaborations between physicists, engineers, and mathematicians foster interdisciplinary research that fuels innovation across various fields. Future discoveries in particle physics hold the promise of revolutionizing various aspects of our daily lives. While some of these advancements may seem distant or abstract, their potential impact on society could be profound. One area where future discoveries could have a significant impact is in energy production and storage. Breakthroughs in particle physics could lead to the development of more efficient and sustainable energy sources, helping to address pressing concerns such as climate change and energy security. For example, advancements in fusion energy research, inspired by the study of plasma physics in particle accelerators, could one day provide a clean and virtually limitless source of power. Discoveries in particle physics may lead to advancements in technology and computing. The development of quantum computing, which draws heavily from the principles of quantum mechanics explored in particle physics, could revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Quantum computers have the potential to solve complex problems exponentially faster than classical computers, opening up new possibilities for scientific research and innovation. Ethical considerations in particle physics research, while offering immense potential for scientific advancement, also raises several ethical considerations that warrant careful examination. One such consideration is the allocation of resources. Particle physics experiments often require substantial financial investments and access to sophisticated technology. Critics argue that these resources could be better allocated to address pressing societal issues, such as poverty, healthcare, and education. However, proponents argue that investing in fundamental research can lead to unforeseen technological breakthroughs and long-term societal benefits. Another ethical concern is the safety of particle physics experiments, particularly those involving high-energy particle accelerators. While the likelihood of catastrophic events occurring as a result of these experiments is extremely low, some worry about the potential risks, such as the creation of micro-black holes or the release of dangerous radiation. Researchers and regulatory bodies must carefully assess and mitigate these risks to ensure the safety of both experimenters and the public. There are ethical considerations surrounding the dissemination of knowledge and the potential misuse of scientific discoveries. Particle physics research often yields valuable insights into the fundamental workings of the universe, which can have wide-ranging implications for technology, medicine, and other fields. However, there is a risk that this knowledge could be weaponized or exploited for harmful purposes. Scientists and policymakers must consider how to balance the benefits of scientific progress with the need to prevent misuse and ensure responsible stewardship of knowledge. There are ethical questions related to the international collaboration and distribution of research findings in particle physics. Collaborative efforts among scientists from different countries are essential for advancing knowledge in this field. However, issues such as intellectual property rights, data sharing, and equitable access to research opportunities can arise, particularly in cases where resources are limited or disparities exist between nations. Ensuring fair and transparent collaboration is essential for upholding the principles of scientific integrity and promoting global progress. While particle physics research holds tremendous promise for scientific discovery and technological innovation, it also presents complex ethical challenges that must be addressed thoughtfully and responsibly. By considering these ethical considerations and engaging in open dialogue, scientists, policymakers, and society as a whole can work together to navigate the ethical complexities of particle physics research and maximize its potential benefits for humanity. As we end our journey in contemplating the emergence of particles from what appears to be nothingness, we are confronted with profound philosophical questions that transcend the boundaries of empirical science. Perhaps, in the cosmic symphony of creation, there lies a deeper truth beyond the grasp of our current understanding, a truth that speaks to the interconnectedness of all existence and the infinite potential inherent in the fabric of reality. Could it be that particles arise not from a void of nothingness, but from the boundless reservoir of possibility that permeates the cosmos? Ultimately, the question of how particles form from nothing invites us to contemplate our place in the vast expanse of the universe and to embrace the wonder and mystery that surrounds us. It challenges us to expand our minds beyond the confines of conventional thinking and to embrace the boundless possibilities that lie at the heart of existence. Do you think particles came to life? How did it all start? Share your thoughts in the comments below. Thanks for watching.